do a project making a reflector as cheaply as possible. So I found this whole way shaving there. And then good job.
I've been looking at makeup hanging, in the grocery store. They're getting better and better. I think if I might have,
I made a decision to look.
Newest number of cats and a lens off the side like hers.
Okay, thank you.
I haven't tried it yet. So you actually tried it?
It's only pulsar observations. I'm sure they're much better.
I asked about the
And a couple of
Maybe
healthy for this one. Monte Carlo analysis. They made a real
The ones that you magnified enough, you don't catch yourself.
Yeah, exactly.
University of Arkansas.
That's an interesting thought.
No, not a different branch of the family. I'm not part of that.
Yeah, could you make a decent eyepiece out of a pair of high magnification green glasses?
Yeah.
Goes on here. It's so much. Everybody's seriously,
It's 2 hours.
presentation.
Hello, everybody. Welcome to the 2017 SARA Annual Conference. Thank you for coming. We're sure glad to see everybody here. I think we got a pretty nice turnout this year. I think we have a pretty good lineup of speakers too, and we have an outstanding keynote speaker, Professor Dale Gary from New Jersey Institute of Technology. I don't see Dale here. I'm sure he'll be here a little later. I would like to thank everybody who's helped out with the conference again this year. We have a ton of work to do to make these things happen. First of all, Janice and Charles Osborne. Charles, is Janice here? Or she?
She's out with the ladies on
Ladies here, okay. Gary Memory. Where's Gary? Oh, Gary is back here. Gary puts together our proceedings, and which is a big job because we always have things coming in at the last minute. And Gary and I are, always a little bit in panic mode. It seems like in the last few days, getting it all together. But again, Gary did it. Gary, you supplied the treats for the back there treats, treats and coffee and so on. And Gary is also our official photographer again this year. So thank you. Bill Dean. Yeah, Bill has put in probably more work than anybody else, I think, to get the conference together. Bill's our treasurer. And it's just a lot of phone calls and emails and so on, communications to get everybody registered for the conference. So thank you, Bill. Steve Jickus. Steve, where's Steve? Oh, there he is. Okay. Steve is our SARA Sections Coordinator, and every Sunday evening he also does a presentation on the Skynet program, which is really nice, something we can participate in. Chip Sufisci, working on the last of what we hope are the technical glitches for the conference. Chip's outstanding work over the years has helped us put the conference online. Ed Harfman, right there, does training every Sunday on Introduction to Radio Astronomy, and Skip Curley. Skip's out. Skip does the, oh there he is back there, does 40-foot telescope training. So I believe that's everybody who contributes. I haven't left anybody out, have I? Good. Sue Ann Heatherly on the Green Bank Observatory side has helped us over the years, and we really appreciate her help. Our keynote speaker, as mentioned before, is Professor Dale Gary. He's a solar radio astronomer from the New Jersey Institute of Technology, and he's going to give us a really nice presentation. Lynn Crowley does the ladies outing, and I think if you want to attend that, that's where the wives who aren't necessarily as interested in the proceedings here as we are can take a little tour. I think Lynn has something planned for 2 days, and they go around and visit tour sites in the area. Schedule, we have lunches and dinners at these times marked on schedules. We have Bill Dean has set up a little SARA store that we have every year back there with SARA merchandise, shirts, past proceedings, CDs. Then at 6:30, we have we set up lawn exhibits. Tonight we need some help setting up our radio show antenna. Ken and I bought the big one that Bill and Linda Lord would set up every year. and we could use some help out there. We didn't get to it last. So, I think I'll cut my remarks short, mostly because I don't have any more, and also we're a little short on time this morning, so I'd like.
We're right on schedule.
Okay, well, I'd like to have more time for presentations. I've only got 40 minutes scheduled for the presentation this morning. I think if you know, I keep it a little short.
That'll be fun.
Yeah, I would.
Thank you, I'd like to say I'm the entertainment for this morning, but no, I won't do that to you. Yes, we have to have notes. Anyways, thank you for all coming. And the one thing we're going to try this year is I'm going to put something together for the hearing impaired. I tested it last year, or I tested it when we were at the VLA, and when I did, the gentleman wasn't there that I was going to test it with, but he's here today, so I'm going to test it today, and hopefully it will work fine. The other thing was, let's see, by the way, one of the things I'm trying to do, we are going to next year, or not next year, but SARA West will be in Stanford 2018. But we had 58 people at SARA West when we were at the VLA. So it's about the same size as SARA East. So I've always what I started to do is I call it SARA East and SARA West. I don't call it regional anymore because it's getting that large. And that's the way I want it to be, because there are people on the West Coast that will get them involved, and we'll have a board meeting there as well, which we will be having tonight. And I did get a phone number for those to dial in if they need to. I don't know if anybody's familiar with Arcaden. That's what we use at my work, and this seems to have the same interface as ours does. So we're getting that sent out to those that are remote. The board meeting is at 7 p.m. tonight, and it'll be in this room. So for those who want to join, please. Of course, the opposition, you don't have a choice. I wanted to thank those also, Astronomy on the Wall. I think they have the largest attendance.
It was pretty big this year.
Yes, and we've gotten involved over the last 2 or 3 years. Steve has picked it up. Chip has also gotten involved with it, and what we're trying to do is, I used to try to get out to that, but it takes a lot of time, so I'm trying to tap people that are geographically closer to that type of stuff. I don't know if any of you are familiar with the Hofstra has an event that they do on the Mall in Washington, D.C., and it's mostly visual for astronomy, visible, but we get interest. People come by. We got the
NRAO is there too. They have a big table.
That's true. That's true. In the NRAO. Were they there this year?
Their Charlottesville branch was.
Okay, excellent. I know they were the year before. Let's see. We had an interesting over at, I don't know how many got to go to. Well, it's not Dayton anymore. It's Xenia, but the convention. And that was interesting. We almost got flooded up, but fortunately we had enough boxes to put things on top, so we didn't have a problem. But it was interesting when it rained. We were in a tent this year, so.
We were right by the drain.
Yes, we were right by the drain. So it was quite interesting, but we got a lot of visits. I want to talk briefly too. They're now talking about possible dates for next year, 2018. The interesting thing is we are now entertaining the thought of doing a combined conference with the Radio Joe folks, which I'm a big fan of that. I think that would be great. And we would combine it with our SARA East convention. The date that we're looking at, and you might want to jot this down, is in June the 10th through the 13th. The interesting thing is they're putting us in front of the Star Party, or the Star Quest. So I'm kind of a big fan of that too, only because usually there's between us and them, usually somebody doesn't leave the room when they're supposed to, and we don't get the room that we were supposed to, or we were told we had. So
I think the only consideration for that is we have a lot of ham radio operators, so they like going to field day, which is sometime in there. I don't know what it is.
The end of the month.
The what?
The end of the month.
That might also impact any school-age kids that might want to come.
Oh, doing it at the 10th, this close to that time. Yeah, this is true. But everything is up in the air. This date was sort of a, and then she said if that didn't work, then she was looking at the second week of July. So, I think what I'm going to do is I'm going to have to talk, I just want to find out, I'm ignorant. I want to talk to the lady and say why, because we did have 1 or 2 rooms that we were told we had, but people were still in them. So, all right, so you got the dates. I also want to say we're going to be mentioning CubeSat this meeting. That's something that we're hoping will take off. But one of the things I've been working with Wayne McCain on that. One of the things we're going to try and do, though, is do the balloon first. We just want to do something so we can at least see the show. We can collect data from a device up in the air. So that's something we would like to work on as well. So that's going to be coming up. I mentioned the Radio Joe Combined Conference next year. I'd like to hear any input on that, pros, cons, whatever. We're a big fan.
Hey, Ken.
Yes, sir.
We probably ought to bring that up before.
Okay, we can do that. You mean the, oh, the combined, yes. Yeah, that's right. And we, because we brought it up last night, but we can do that before. Okay.
Jim, should you have one day to the conference if you're going to combine it, or?
Well, what we talked about is we would almost streamline it. We would keep it the same length, but we would give them a half a day. That was the thought.
Okay.
And we're open to suggestion. We're just trying, but it's just, I'm geeking over the fact that we could do something together with them. And they do it about every 3 to 4 years. They like to do something. So, and the other thing is we're talking about bringing in Dick Flag as well, which, you know, that's kind of a, I know he's kind of a rock star in radio astronomy. So, yes, sir.
If we proceed, StarQuest people start coming in on Tuesday, we need to have the rooms reserved before they start reserving. Or we're going to end up not having rooms,
The same.
as we have in the past.
Okay, well, this is coming from Suzanne, and I will...
No, I understand,
Right.
but all I can do is tell you, when we proceeded in the past, they would get the rooms starting on Tuesday. We couldn't get the rooms. So the lawyer did well.
Yes. Yes. So what I will do, though, is I was going to reach out to the lady that does the rooms and just start making her as well.
Just reserve all of them through the Wednesday before we leave here.
Okay, because we would be here till, like, we would check out Wednesday.
Yeah. So just check with Christine.
I should do that now. Okay. Again, this afternoon at 2 o'clock, or I'm sorry, 1400 we're having a keynote speaker will present. And then at 1900 tonight is the Board of Directors meeting, which will be in here. And then, of course, we'll have tomorrow morning at 9:30, which will be a summary, which will be the board meeting, or the business meeting. So we'll give you a summary of what took place tonight, if you don't know. So, I finished.
Thank you. Okay, Steve Zizikas, or Jikas, I mean, that's how you say your name. We'll update us on the SARA sections, which are groups that Steve has set up to specialize in particular aspects of radio astronomical observation.
We have live streaming now on the internet, so the speaker should come up farther than this position. Right? And you're fine from here to here. It's fine. And all the screens is available.
I know Dick Flag wants to see this. Is it right on the front page of the SARA website?
There is a big link on the home page to watch on YouTube Live.
Okay, I'll email when we're done. Thank you.
Yes.
Okay. Thank you, Tom. So SARA sections were set up a couple years ago The purpose behind them was to make the SARA website similar to other amateur and professional scientific and engineering websites. Perhaps you're familiar with some, you go on and they've got different sections of topics of interest. So that's what we've done here. The sections help make it more conducive to volunteering, database collection, strategic planning, creating observation protocols, maybe engaging in meetings of interested members. These are ideas that we'd like to bring to fruition in the future, so we're just starting with them now. The organization, if you look at the sections, it's all volunteer efforts. So whether you're new to SARA or very experienced, we'd like to post a lot of different documents that might be useful to the membership. So if you have documents that in your personal files that you'd like posted, get in touch with one of the section coordinators. We're taking a Wikipedia approach to this, where we're posting something out there for the members to review. They can in the future add to it and grow those documents. As we develop the 6 SARA sections, we noticed we need some management and professional guidelines. So we've developed that area on the web page too. You'll find the sections, the top ribbon on the SARA website to the right has the SARA section. Towards the left, you'll see the ribbon with the administrative there that has the management and professional items. And then if you're looking to get interested in the SARA sections, there's a lot of tools. You don't have to be very experienced. When I started this, my incentive was I wanted to learn about radio astronomy. So I was doing a lot of research and thought it was a good idea to create the sections. Some of my sources, which are all available to you, most of you I would assume are on the listserv, so a lot of great ideas there to maybe compile into documents. We put together a SARA section team to help the coordinators with advice and discussion on what can you post and how do we post that. And of course the internet is a great source of information too. So the organization of the SARA website, when you click on SARA sections on the ribbon, you'll come to a first page. There's a lot of beginners information there. That was one of the suggestions for the first year. Participants thought it would be great if we could put a lot of the beginner radio astronomy information there, so we did. And then we have the other 6 sections, which are listed on one of these slides. I think the idea is to fill out a lot of information on the SARA website. There's gaps on the website as a whole, so this is where we can maybe input post information, observing protocols. One of the things we're looking to do is try to create a SARA data template that collects standardized information. That's easier said than done, but we're trying to do that. And under the solar system, stellar and galactic sections, there's some draft templates there that we've started. They need to be developed further. Volunteering, I talked a little bit about that, but this slide shows the different things. If you're interested, contact one of the coordinators. There's a lot of subtopics there, so there's always a need for sub-coordinators, assistant coordinators, so a lot of room to participate. Section coordinators, we've just assigned them within the last few weeks. The only one that couldn't make it to the conference here is the solar system section coordinator, Rick Reeve. Many of you have heard his name. He's one of the SARA Journal contributing editors. I'd like to say something about his site. He's asked me to, let me bring up the He's just posted a new link for the total solar eclipse on August 27th, so that's some new information. Click that and then find additional links here you might find useful. If you're planning to take measurements, please send your information to him. He'd appreciate it to compile it, and I'm assuming with the intent of posting it. And then the other coordinators in the room, we have Tom Crowley in charge of the outreach section. We have, where's Skip? Skip, yep, in charge of the Stellar section. We have, where's Dave Westman? Is he here?
Yes.
There he is, in charge of the Galactic and Cosmology section. And Bogdan in charge of the Electronic and Instrumentation section. Where is Bogdan?
Here.
No, okay. If any of you would like to say anything, that's fine on your section. You're welcome to. No?
I could say some stuff. So I've compiled over the course of my interaction with SARA for the last 5 years. I've compiled a lot of links and informations to like calculators of antenna power and system design references, noise. I've compiled lists of information that has helped me in, like what Whit presented at the Western Conference in terms of analyzing the system. So I plan on putting all those links and kind of organizing them in a way that I described at the Western Conference last spring. So I'm excited about it, and so contact me with your research, because no doubt everyone has sort of built up a treasure trove of really important papers or websites that have helped them build their radio system. So please send those to me, and I'll collate them into the section information.
Yeah, Bogdan and I are trying to, and a few others, trying to put together an observational radio astronomy program, and working through some of the difficulties for that. And Dave Westman, you were at the Western Conference too, presented there on your Galactic and Cosmology section. Let me just one. I was going to say for your section, Tom, there is in case of any of you that do outreach for SARA or radio astronomy, you can make me aware. If not, I'll show you where the links are now. There's 3 SARA brochures. That's these outreach brochures here. And you can click onto them, print them, so you've got one on the SuperSit program. I use them when we do outreach. I print them double-sided, and the public appreciates them. There's the general SARA membership brochure, which goes into a few of the different observing programs. And this one's popular with teachers because it talks about the SARA grant program. So they're all in one place now. You can easily download them. And here's the administrative link. So all SARA sections are up here. The administrative link here. There's a lot of good stuff under management. There's some historical information on SARA we've started collecting, which should be a couple places. So most of the presidents that can be developed further. SARA's and some of the past meetings with SARA and the SETI site. And then a professionalism section, code of ethics. websites, SARA lists their rules of contacts, volunteering, professionalism statement. Any questions on the section? I mean, we look forward to your participation. Just contact one of the coordinators. Anything you'd like to see on them, maybe, and we can try to get? Okay, thank you.
Okay, great. Thank you, Steve. Skip Crilly will be speaking next. Pulsar observations at 1400 megahertz using the 40-foot. And maybe a second topic too.
Yeah. Impossible for me to avoid. He knows it. It'll take a second if you want to first. Yes, he admits it.
By the way, I'm going to throw in 2 cents real quick. They're having a little bit of issue with the payment system and writing up invoices and things like that. So today you won't be able to pay for your room. They're hoping they're going to get it online by tomorrow. So just FYI.
They know it's free.
What's that? Yes, it's free, right, yeah. We're not the government.
I'm just giving them an eye on it.
Here's some pulsars.
Okay, good, it's all set. So I'm going to talk about pulsar observations at using the 40-foot, 1400 megahertz. And then I've got some SETI slides. I can't avoid, I always attach these SETI slides. So you know, because after 3 years now, I've been 5 or so lectures, these talks, I always throw in some SETI slides again. But I was coming across the country from California here over Christmas time, after Christmas. And I was thinking, I wonder if I could use the 40-foot to see some pulsars. And I thought about what I needed, and then I realized, I think I have everything in my car to do it. Well, I was missing an op-amp amplifier. They have parts here, so I was able to build that up. So I thought about how to do it, and then I realized only 4 minutes, everything has to be just right. And the pulsar goes to the beam. So when I got here, which was right around the new year, before that I started setting up and designing the system. And then I think these observations were right around January 1st. So I'm going to talk about that. I'll go through that. I'll explain what pulsars are and how they work, why they transmit, why they're so energetic. And then the system it takes to do it, you can replicate it pretty easily. It's not a complicated system to receive pulsars at home. And then I'll go over the SETI things that I've been doing.
Jim,
Yeah.
can you speak up just a little bit?
Sure. Okay. So a pulsar is what's called a neutron star. And this is a schematic of a neutron star. The supernova collapse creates the neutron star. It's spinning. Has a lot of magnetic field. And this is a potential source of radio energy. The atmosphere of this is extremely small because the density of a neutron star is so high that it has almost no atmosphere. It's about 1 millimeter thick, but there is an atmosphere, about 1 millimeter. And that atmosphere is made up of quarks, protons, and neutrons and electrons that have escaped from essentially what is a gigantic nucleus. In this case, this one's 20 kilometers in diameter. Okay. So they're very big and they're small. And it's like thinking of a nucleus without the electron cloud around it. Just to give you an idea, I got the smallest font I could figure out how to put right there. And that dot represents what the neutron star would look like if that was a sphere of the Earth's density. So basically, it's Earth's density over there, 5.5 times 10 to the third kilograms per cubic meter. If you compress all that down to this, you'd still be a factor of 40 short, because the density it needs to be 40,000 diameter, basically. Diameter 40,000 times smaller than that. It turns out this dot is only 1,000 times smaller. So I've been told that if you take all of humanity on the Earth and compress it into a sugar cube, that would be the density of a neutron star. Okay. So as I mentioned, they're not really all neutrons. If they were all neutrons, there would be no charge. And of course, when you accelerate charges, that creates photons, which creates the radio energy received. So they have to have other particles, and those particles are gluon. Potentially, some of the models have that there are a lot of gluons in there. The surface speed can go up to a quarter. Well, or an example could go close to the speed of light. Quarter the speed of light at the surface. So a bunch of these calculations that we would normally do for radiation, they have to use relativistic equations. And I'm just using an example over here. Now, if you have rotating charges in that little 1 millimeter surface, and then if the charge is able to escape through a magnetic field out the surface, they're going to generate a magnetic field around the rotating charges. Then that magnetic field is going to suck up the particles, charged particles, and they're going to go circling around out the neutron star. And in this example, this formula is the force on an electron, the charged particle, is the charge times the electric field plus the charge times the velocity of the particle relative to the magnetic field crossed with the magnetic field value. So this is the right-hand rule in electromagnetic theory, and you can use this to predict what will happen when you have a magnetic field moving across charges. Where will the force point? And this can be used to show that charged particles will tend to circle around the magnetic field lines of moving when they're moving with respect to each other and create that force. So the kind of standard model of a neutron star is that it has these radio beams that are the result of charged particles that have left the surface and are spiraling on the cone surface. And some of the models show and some of the measurements show that the radio beam, when it crosses us, is really a disk of energy. So the pulse will be fairly wide because we'll get the whole disk. And other ones you get double peaks, in which case there are cones of energy that are going. And that's why sometimes the pulsar shapes have like double pulses to them. And they're very dispersed through the interstellar medium, which is a lot of electrons. And those electrons cause the higher frequencies to arrive sooner, and so there's dispersion, which means if you want to measure a pulsar over a wide bandwidth, you have to do what's called de-dispersion. So you measure what's called the dispersion measure for that pulsar. And if you're looking over a couple hundred megahertz of bandwidth, then you have to correct for that so that all of the frequencies of pulses fall on top of each other. Otherwise, it gets smeared out. And we can't quite see it as well. Turns out they tend to be very strong around 400 megahertz, and then the flux drops off. So it's a little tougher to get pulsars up to 1400. The advantage of 1400 is for the same bandwidth, the percentage bandwidth is smaller, and so the effect on dispersion is less. So it's a little easier to do the signal processing. And in this case, I didn't de-disperse at all. I just used 50 megahertz bandwidth. But if we were down at lower frequency and wanted 50 megahertz bandwidth, we might have to de-disperse to get the pulse. Let's see. Okay, so that's how that works. And here's some sounds. Hopefully this will work. Let's see if I got everything turned on here. Volume is turned up. Then I can turn down and I can adjust it. Okay, I think I have the volume turned down. Yeah. Let's try that. Sorry about that. Let me test this first. Let's see. So this is a typical normal pulsar with a period of 0.714 seconds. This is what I measured using the waveform, this particular pulsar. Okay. 1.4 rotations per second. Okay, so now if we go to, this is a pulsar, the Vela pulsar. 11 times a second. And then it fluctuates a little bit. Here it's going down. 30 times a second. Okay. Now we're going to go up to 174 rotations per second. Pretty amazing to think about this 20-kilometer nucleus rotating 174 times a second. We just happen to be lined up with beam. The beam just happened to process. And of course, there's tens of thousands of these out here. And now we go to this one is the fastest known pulsar rotating. These are called millisecond pulsars. They're very old. I'll talk about that in a minute. This one's going at 642 tons a second. Each of those is a pulse. Okay, so that's a lot of fun. These sounds are all on the web. So all I did was I just pulled the links off. Yeah.
The last one, there seemed to be, it wasn't like a perfect tone. There was like doo, 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 doo. Did they know what that is?
The pulsars have these, like the equivalent of the moon with vibration, where it has like wobbling going on, things going on. And there's so many models. Sometimes, I mean, it's incredible what pulsars do. They're just fascinating. Sometimes the pulses will completely stop. And if they record and look at it, in one pulse, there's one pulse, and then they are absolutely undetectable. And maybe a day will pass or 2 days will pass, and they'll come back within one pulse. They don't go up slowly. They actually reappear on a pulse after a long time. I thought, it's weird. I think there's things that happen that force the magnetic field to take some kind of a jump, and then it returns back to another state, back to the original state.
I mean, is it when it comes back on, is it exactly in sync?
Yeah, I mean, I think so. I'm not an astrophysicist, but I think that, it'll look just like it was an outage. It could have been an eclipse event or something.
Yeah, I read they were saying other stellar bodies between you and the pulsar are getting in the way, and that's why you're losing the pulse.
Right. Yeah, it's fascinating how that all works. Okay, so this is what's called the pulsar P dot diagram. This is pretty much the standard way of looking at how pulsars can be categorized. And they start very young, the early pulsars, right after they become neutron stars, the crab was, what was that, 1054?
1054.
Yeah, so in 1054, the crab supernova exploded, and then that was one of the first pulsars discovered. And then they said, okay, so this is time, this is age, estimated age. This is magnetic field, stronger magnetic field, weaker magnetic field. And this blue area is the region where pulsars will pulse, will radiate. And then some of them will fall out and fall into the graveyard of pulsars. These are the millisecond pulsars, so this is period, and this is rate of change of period. So when pulsars were first discovered, they measured them against the cesium clocks, and they couldn't tell if they were slowing down or they weren't changing. In fact, they appeared to be more accurate than cesium clocks. As time went on, they found out, no, they're actually moving, and now they can measure all of them. And there are very few down here. These few are about as accurate as the best, as basically the standard hydrogen masers. So they get to be a little tougher to measure when they come into this region. But, and okay, so and the other thing I just want to mention maybe is that these are, the timing of pulsars is used in the nanograph project here. So they look at thousands of pulsars all over the sky, and if two black holes fall into each other, they can use the LIGO interferometers to detect the gravitational waves that come from those falling, two black holes falling into each other. And that's been done now. We've got two, I believe it's up to two now, for three. Okay, so 3 discoveries of gravitational waves going on. And the nanograph project, which is going on now using time on the Green Bank telescope, is a measurement, another way of measuring that. Because the pulsars themselves, the waves that are traveling from pulsars from different directions, those waves will travel through between where the source is and Earth, and they will modify space-time during that time. So the pulsar shape will change, it will wheel, and they can predict how much that wheeling is. Okay. So this is what I did to build this system. So this is the 40-foot, everybody knows about that. This is a schematic of the system. So I want to keep it simple, but I decided, to use an external square law detector. Now, there may be a way to use the one that's built in there, but I took this. This is basically the same device that's inside here. The one in here is from the 60s, and this is a modern one that they still sell. Shocking detector that basically has the same model number. Maybe it's a few numbers higher, 423D. And you can get these on eBay, and you can get used ones. And they're quite good for power detectors. I put some amplifiers in there. I'm going to tap off one of the tap points on the IF tray. So you can put that in there. And the attenuator is just a handy thing to have, just to control levels. The bandwidth of the signal is shown here at the IF. Okay, so we want to get as much IF bandwidth as possible. And it's about 100, I think it's 150 megahertz or so, maybe 120, 130 megahertz roughly. Now that goes into a detector. This is a load that you can get from Keysight that will essentially cause the detector to be square law, very close to square law in power measurement, calibrated. And they measure that, and so that it matches. I think it actually is a match to the actual diode itself to get those together and put that on there. And then I go into the same pico digitizer that I used for SETI and for the interferometer that we built here last year. But now I'm using this at a very low frequency. So you don't need an expensive digitizer to do pulsars. If you can do something that's got audio bandwidth, audio capture bandwidth, 20 kilohertz, it'll work fine. And in this case, instead of, I didn't have to do all the code, all the C code, to get the fast data off the pico digitizer. So I just used the standard program, the scope program that comes with picoscope. And I just saved at the sample rate that I chose the waveform in picoscope software, and then I put it into Excel. And then I use Excel to algorithmically look for the pulse. Now it turned out that I needed an amplifier between the detector and the picoscope. The picoscope noise was a little bit high. So I put this op-amp amplifier in there. Just a standard, this is a standard non-inverting opposite 107. Fire. Now, the way we process this is probably, I think, the most basic pulsar detection algorithm, which is, we call it overlap and add. You take a whole bunch of periods of pulsar, none of which can really be seen individually on the 40-foot. In a bigger telescope, you can actually see the pulses come up out of the noise really nicely. Can't see it quite. I barely see some of them appearing above the noise, but you can just average it out. So the noise is way up here. Pulsar's down here. This is power time. And in this setup, I take 117 periods of the waveform of the time domain data that's stored in an ASCII file that I then bring into Excel. I take 117 of those and overlap them. So basically just put every 117 of these samples, which turned out to be 1,000 samples, I believe, that came out. But they're spaced at 0.71451 seconds. So in order to easily detect pulsars, you want to use the period. Okay? You want to say, okay, I know this should have this period. Now, the very exotic systems that they use here will find the period out by doing fast Fourier transforms and looking for the pulses within the record. And just pull them up out of the noise and then report the period. Well, for this system, I kept it simple and I just said, all right, I know this one is at 714.51 milliseconds. So what I'm going to do is just take that and overlap and add that, and then of course the signal comes up out of the noise after we add a lot of it.
Skip, how do you get the sampling process exactly lined up with the pulsar, right? Because if it's a little bit off, it'll be
so it turns out,
different parts of the pulse.
I'll answer that because I'll show you what happens when you don't. So the idea is to figure out what the pulsar shape or what the pulsar period is, or guess it, or read it like I did. And then make sure that the samples you have are exactly the pulse period. That causes the pulse to be in the same location within each one of these little windows.
So you control the sample rate of the ADD converter.
Well, the ADD runs at like 10 kilohertz. But then within Excel, I get all the samples. And then I grab a certain number of samples here, 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 here. And the number of samples that I grab in the long thing to overlap and add is based on the 714.51. So the width of this from here to here has to be 714.51 milliseconds. Can I answer that?
So since the sample rate isn't exactly a multiple of that,
yeah,
you get a little bit of jitter on the on the pulse.
And I think I sampled at 10 kilohertz. So this has a lot of samples in it. And then I take 117 of these windows of samples to create a 0 to 1,000 phase. Now, normally the phase on the pulsar is reported in 0 to 360 degrees. That's kind of the standard. The way this worked out, I rigged it up so that 1,000 samples would correspond to the full phase. So this goes 0 to 1,000. It's just another way to represent the phase of it. Now, you don't know, before you see the pulsar come out of this process, you don't know where it will be in phase. Okay. It could be anywhere along there, but then it just comes out. So this is what I did, and then this is an example that when I adjusted 714.51 milliseconds in the spreadsheet, which I can give to everybody, if anybody wants a spreadsheet, I can just give that to you and use it. When I got, it said 714.51 milliseconds, and then there's some numbers here about how I did it. In this case, it was the 70th to the 187th pulse overlap add. That's of the entire record. I went through the record because I didn't know exactly where the pulsar was on the antenna, but I knew I was somewhere in this 10-minute capture that I took, roughly. And so I moved a window along 70 to 187, searching for where I got a good peak. And this is where the peak popped out. This represents now from 0 to 1,000 the full phase of the pulse. So if the pulsar is repeating, it'll repeat at the same, at the same place in the phase. Okay. Now there's a tiny little secondary glitch right here, which, I worked with Ryan Lynch and I showed him my slides and he said, oh, let's look up the GPT. And this pulsar does have a second little peak right about there. So it's like that cone, as the cone moves through, there's some other little lobe on the cone or something that's going through too. And it's very clear because the noise level is like that axis line right there on the GBT, where this has all this noise. Okay, so now to answer your question, if I plug into the spreadsheet a different period, oh, this is the time domain data, unaveraged. So you can see kind of unaveraged that there's a bunch of peaks right there that occurred, really high peaks. This is each one of the samples just kind of overlap on top of each other, but without averaging. And then yes, to answer the question about, so this is if you plug into the spreadsheet 714.31 milliseconds. See how it's all smeared out, and it's spread, and it's also moved. So that just says that what happened was all those pulses that were on top of each other are now no longer on top of each other because we applied a different window. The window is 714.31 instead of 5 now. Okay, so it's smeared them out. And then this one is when we go the other way, 714.71 milliseconds, and it smears in the other direction. So knowing the period is very important. Okay, so yeah, that was January 1st of this year. So I wanted to see if I could see a second pulsar. It turns out one of the strongest pulsars in the sky is about 5 degrees below the lowest point that the dish can go, the 40 foot. Okay, and it would have been a good one. But it turns out I think these two pulsars are the only ones that are within the field of view of the 40 foot telescope that I thought I could detect. So then I worked for my second one, the 40 millijansky one. And that one, I thought I saw at the period, at the correct period, a pulse right there. And I thought I saw another pulse over there. Of course, this is, it looks pretty good in the individual data. You see how it's multiple points here, multiple points there. It looks pretty good in that, but in the averaging, it doesn't look so good. So I'd say this is kind of inconclusive as to whether or not it is. I did show this one to Ryan, and Ryan said that looked it up, and sure enough, it is a double pulse. It has the second pulse in it. But as I stated, he said, well, yeah, it looks like it might be there. And, we're just not sure. I'm not sure it's there. It's a little inconclusive because there's so much noise. 40 millijanskys. So the idea is, of course, you have to track if you can. Right? Tracking a pulsar is like the #1 thing. Yeah.
But why do you avoid using the FFT to get it directly?
I was just throwing it together. This was quick. So the way to do it.
But you've got all the raw data.
Well, it turns out this method of averaging probably produces the same signal to noise ratio as an FFT. It's possible. Because I used all of the data I could to produce these overlapping apps. Now, if I used an FFT, it could have found the pulse for me, but I already knew what it was. Because these things are known to like 11 digits or something of ridiculous. They know these pulse rates because they're measuring the P dot, the P count rate of change of the period. So yeah, that's
it would be interesting to see your data run through the FFT.
Yeah, well, it gets a little tricky with the FFT, and I have to disturb it. Because the shape is not a sine wave, it's a pulse, it turns out you're going to end up with pulses in the frequency domain as well. So it turns out each one of those pulses after you do the FFT really could be also having fairly low signal-to-noise ratio, depending on the width of the pulse compared to the overall period. So what happens is that you've got to go, okay, well, no, we need a little more sophisticated algorithm, which says we're going to look at harmonics as we scan along the subharmonics as a fundamental. We then have to integrate, power integrate, with wherever the harmonic of that frequency is to get more signal-to-noise ratio. Essentially, you want to combine bins and the FFT. At least that's what I just thought of that. I'm just thinking of that. It probably might be the method that's used, I'm not sure.
A few years ago, there was something going around, some signal processing, some kind of wavelet transforms.
Yeah,
where instead of using
might
sine
be
waves, you used other shapes, but a similar algorithm to FFT, and that could prove more appropriate.
I think that's actually it. It's a transform that's based on the shape of the pulsar as opposed to a regular FFT, which is based on sine waves. Let's see. So that's inconclusive. What is this? This is, I guess I'll try it another day, maybe. Oh yeah, it looks like February 2017. I think I tried it again. Is that a second one? Another look, yes, okay. So it's the same pulsar. I did a second look. When was this one? Oops. Oops, I went the wrong way.
Any possibility of
This one
averaging
was,
multiple days?
this was January 2nd. So then when I went back to Green Bank again, I wanted to look at it again. And that was this next one. So this was February 27th. No, that's the February 27th one. So that shows kind of the same kind of peak, same kind of, you know. This was the previous one, and this was the new one. So again, we can't find out where it's going to be in phase, right? But it looks like there's still something there. In fact, the deltas between this peak and this peak are 475 going one way and 525 going the other way. And this one turned out to be 496 and 504. So this might be the 40 milligems to pulsar. Yeah. Okay. Okay, so that's it for pulsars. I'm going to move on to the SETI stuff. That's okay. Are there any questions on pulsars? Yeah.
Were you able to measure dispersion measure at all, or anything at all?
No, because I had just baseband and I just had the detector running, so I had no frequency information. To get more advanced, we would digitize, right? The advantage of the detector is I was using the full 130 megahertz of bandwidth that the detector was being fed. If I used my digitizer, I'd be using 45 megahertz, although I could push it. There's probably ways I could get the bandwidth up. And then there's the issue of the duty cycle, which my software, the picoscope, has a third duty cycle. So that would also reduce my signal to noise ratio, so I would get it in samples. So, but with good digitizers, yeah, that's the way to go. And dispersion, and de-dispersion. Especially if you go to lower frequencies. Now, 400 megahertz, you get a lot of flux, but then you got to de-disperse it, so usually.
Those picoscopes, how much do they go for?
You can get them from all the way from about $200 to $300 or so for the baseband versions that have like a 50 megahertz maximum bandwidth, I think, or maybe 20 megahertz. And they'll go up to thousands and thousands of dollars. This particular one is, I think, around, it's a little over 1,000, something like that.
Okay.
I don't know the exact price, but it depends on what you want. I wanted a USB 3.0 to go at maximum speed, 5 gigabits per second, into the host, to get data into the host as quickly as possible, into the Ubuntu machine. Okay, so as you all know, I've been doing SETI for a long time, and for the last approximately 2 years, I've been bringing my backend, one of my backends from my farm in New Hampshire, I have a couple of stations there, and bringing the backend here, backend meaning the Ubuntu computer that I use to search for triplets. That's I'm like just narrow focused on just one thing basically, which is I look for triplets. That's 3 pulses that come up on 3 different frequencies, and to look at to see if there's information contained within the triplets. About maybe over 2 years of putting the back end on the 40-foot while I was here and running it, I continued to see things that I've been seeing in New Hampshire when the beam goes through 40 Eridani. So this is my 7.6 declination. It's a triple star system. It's off from Orion's belt to the west. You go down and then go down a little bit. It's a triple star system. Now, I've been focusing on 40 Eridani because I see weird triplets that popped up, both there and also with a 40-foot telescope. So I'll just talk a little bit about what 40 Eridani is. The triple star system has a K-class star, which has a habitable zone at around 223 days for the center of the habitable zone of the planet. No planets have been found around it yet, but they've been looking a lot. There's a red dwarf and a white dwarf. So it's A, B, C. A is the star, the K-class star that potentially has habitable planets around it. The B, I'm not sure which is the red dwarf and the white dwarf, B or C. The white dwarf is far enough away from the main star that the ultraviolet is not dangerous to life on a planet around A. So it can sustain life. Normally white dwarfs near habitable planets, they cause all kinds of problems to life because they're very high in UV. It would look like a star about the brightness of the moon on 40 Eridani, a planet going around 40 Eridani A. And the red dwarf is fine, and it's reasonably far away. And of course, red dwarfs are one of the main subjects of searching for signals from extraterrestrials. They're considered now that there may be many, many planets around red dwarfs capable of supporting life and having intelligent life. So I was using the 40-foot, and then about towards the end of May, I thought, I wonder if there are any 40 Eridani breakthrough listen files from the GBT. And I was invited about a month earlier to be on the collaborators team for Breakthrough Listen. And so I call in on those webinars and listen to the progress that people are reporting. About 40 or 50 of us that are on that. So 30 generally call in every month. And I sent a message while I was here to Greg Hadlor, a Breakthrough Listen group, and I asked him if there was any 40 Eridani samples, time samples from the Green Bank telescope. And they said, no, we've overwritten them all. But about 3 days later, I got an email that said, we're going to look today for Eridani. So I quickly went up to the control room, and it turned out it was the first scheduled observation for that day, which was right around 10:30 in the morning, 26th. So I had Dave Woody take my picture there, and I'm pointing in the direction of 40 Eridani, and that's where the dish is pointing also. Right now, the GBT is pointing at 40 Eridani. The time samples, 5 minutes duration, are going into the GBT right now, as that picture was taken. So what do I have as far as the protocol? So I was just kind of say this. Okay, so I look for triplets. The idea is that if you want to exchange information from one place to another, you want to think of, okay, what kind of shared information might be present? Anytime we have shared information, we can communicate with less energy. The second thing is, how can I contain information in as simple and low energy pulse as possible? And there's lots of things that could be possible, and I've just been thinking about it for a while, years and years, I've been doing this for decades. And I thought, okay, how about if you send me one pulse, I'm not sure exactly what to do with it. And I'm going to want to see another one and another one, and maybe it'll come up on another frequency somewhere else. Okay, if it comes up on another frequency over here a little while later, that's called spread spectrum. And that's done intentionally to try to prevent detection. Okay, and that's a very standard system called frequency hop spread spectrum. Well, I kind of didn't think that would be such a good way to do it. Well, if you bring up two pulses, I'm not exactly sure what this means by the spacing between them. Let's say they both cross a signal to noise ratio. So this is frequency, this is power. Two pulses pop up on different frequencies, but I don't know what to do with the separation. It doesn't really give me anything as a reference, and I can't really get any information out of it. But if you put 3, so split the energy by, take a third of the energy, put it in each one of the pulses. If it crosses my signal to noise ratio threshold, and there are 3 pulses present, I can immediately look at this thing and say, oh, I can get a number out of this. I can take the ratio of this frequency spacing to this frequency spacing, and I can create maybe 6 digits of information. I can say, well, whoa, wait a minute, look, it's 3.14159. The spacing. Well, who's doing that? Who's setting pi? Okay, well, as far as I know, this communication system is not used to transmit information as a ratio. Now, there are systems called OFDM, and JT65 is another example, where you bring up tones. The most modern systems of communication today program bits into sets of tones, and they turn out to be the best method to use in terms of Shannon's law. But this is just sort of a subset of that. It's a much simpler form of that, where the information is not trying to be encoded in where the tones are, but just basically the ratio of the frequency here to the frequency here. Now, when I take the numbers and I process them, I end up saying, okay, my FFT has 13 million points. That's what I use for the 40-foot telescope, and that's what I use on my farm in New Hampshire. And when I use the GPT, there are 64 2.929 megahertz channels that are already created in the data. And there's a gigantic file. The whole thing is about 1/4 terabyte for 500 seconds. And that data then, I can look at individual 2.929 megahertz channels, 64 of them, and then process them individually, looking for triplets in each one of them. And so I modified my software to take the Guppy files. Guppy is the Greenbank Ultimate Pulse Processing Instrument, I think this is the acronym, developed here at Greenbank in the Jansky lab. And it's used to look for pulsars, but it's also used by the Breakthrough Listen Group program to create the files that they run for 6 hours on the GBT every day, pointing at different objects. And they're pointing things and also off the objects as well, and doing diagnostic scans and things. And so 1/4 of the time on the GBT is used for that. So I take that file, and that one has, I use a 2 to the 22 point FFT. And overall it produces 0.69 hertz bins. So each channel is 0.698. Now if we take the ratio of 0.698 and say, okay, how many numbers come out of these ratios of bins? I only get about 5 digits, maybe 6 digits of resolution. So when I take the ratio, only the first 5 or 6 digits are going to be significant. So then I go, okay, well, what kind of numbers am I going to be looking for in this? So I've just been experimenting with this thing over the years and come up with the idea, well, again, we're getting back to shared information here. Why don't you send me something that I already know and that I think you might already know? Okay, so the idea is if they have big antennas out there, they're going to listen to us, they're going to hear our emissions and say, and measurements of our planet, and say, why don't we send them something that they already know? So if we agree with each other, even without communicating, that we probably know certain sets of information, why don't we use that? Well, I've sort of glommed onto this idea of using the early Morse codes that were used. So the early Morse code telegraph, wired telegraph, was putting about 200 watts into the end of a piece of wire, which then was repeated multiple times across the country. So you had like thousands of watts of pulses going out from the planet every time they closed the key at one end. Okay? Those pulses potentially could have been received by something as noise pulses. And one day I've got to go through all the calculations to see what that turned out to be. Well, Walter Phillips developed a code in around 1879. He published it, but I think he was using it probably when he was very young and starting to run radio telegraph. He's a fabulous radio telegraph operator. I'm sorry, land telegraph operator. And then he was later head of United Press, because the reporters all used the telegraph. And so he naturally became connected with what was best for them. And one thing he found out was that we really need a dictionary. So he created a dictionary of thousands of words that were taken down to 4 letters or 3 letters. So ENGR, engineer, is in his dictionary. He also came up with President of the United States and Supreme Court of the United States. And what would happen is the reporters would take his code that he sent shortened over the wire, and they'd put it in the newspaper, and they wouldn't change the POTUS, they would leave it there. And that's why we use POTUS today, and SCOTUS today, is because the newspaper wouldn't spell it all out. They just leave it that way. In fact, there are other little artifacts of Phillips codes that appear in newspapers, like 30, sometimes appears at the end of the story. That's the end of message that he developed. He said, this is the end of the story. And so sometimes the reporters would cut and paste, or not cut and paste, but they couldn't do that then. So they figured a way to copy it in, they make up the newspaper, and then the 30 would still appear. Okay, so there's 7.3 and 8.8. We all know this, all of the hams know that at the end of many, many messages in Morse code, 7.3 and 8.8 are used. Well, they're also used in the wired telegraph days and then the radio telegraph days to shorten the messages using the Phillips code. Okay, and I've researched it a little bit, but I'd sure like to find out more about it. Now, the numbers themselves, da-da-da-da-da, da-da-da-da-da, da-da-da-da, etc., can tell someone pretty quickly that here we use base 10, at least for our transmissions. Okay, all right. Okay, I had until 10:40.
Yeah, we're running a little bit ahead, and I'd like to give everybody a little extra time.
Oh, okay, all right, okay. Yeah, because, see, it's 10 after 10, 12 after 10. Yeah, okay. Oh, okay, okay. Okay, we'll go through this quick. Anyway, so that's what I look for. I look for 365, 7388. So this is using the 40-foot telescope.
10 minutes.
Okay, so this is using the 40-foot telescope. And I look for patterns of 365, 7388. This is an example. So this is a ratio between the spacing of the tones, and it's got a 36588. There's no digits after the 365 to the 88s. Okay? Now there's a weird thing happening here, which is that the 88s and the 73s should be separated by 50 digits, if these are random digits. All I did was take the two FFT bin separations, divide them by each other. This is 1 over that number, because I look for both. Because I don't know which way the thing might be. It might be this way, or it could be this way, right? We don't know what the numerator and the denominator are. So, I try both. And this turns out 36588. Well, there's a weird thing going on here. This should have 50 digits of separation between 73 and 88. Well, suddenly, down here, there's another 36588 after these few number of spacings between the 73s and 88s. 36588. And then we're back to this old business of not enough digits between the 73s and 88s. Then suddenly, there's 92 digits after this 88 with no 73s and 88s. Until we get 3652727. Okay? 27 is the Phillips code for priority, very important. Okay, so that's another number I look for. Because I can imagine that in the olden days, the message would be repeated multiple times, and there'd be these 27s all contained within it. If it was a very important news story, there were probably 27s all over the thing. So it could be someone has looked at this and said to do this. Now, by the way, this claim up here is the most important point on the entire slide, is that I do not claim anything about extraterrestrials, okay? I have no hypothesis. I have, the assumptions are all just crazy. All I'm doing is just poking around. This is pre-hypothesis. I don't even have a hypothesis. I'm just observing, okay? And so these are the numbers that pop out. These three tones were 12.457 composite SNR. So I calculated the power in each one of the tones, which included the noise in that tone, and then calculated the noise power, referenced it to 1 bin bandwidth. And that turned out. So this was actually a pretty strong signal. If you're looking on the spectrum analyzer, you're seeing these three tones that are like almost 20 times out of the noise average for the three tones. Okay, so that one was kind of cool. The probability of seeing this, I think I did the math right, I don't know, might be wrong. But the probability of seeing all this kind of stuff is about 1 in 1,000, 1 in 700. And then the probability of the second 36588 after that one, that's really tiny, right? It's 1 times 7, 1 out of 100,000. You're going to tend to see a repeat of the same 5-digit number. Okay, so then that was kind of cool. So then I saw this other one. This is also using the 40-foot. By the way, these were all pointing at 40 Erdani. So I get 5 minutes, and I get about 10,000 triplets that come out. And then maybe 10 of them are 365s for the first digits, because on average, you're going to get 1 in 1,000 365s. So this one was kind of cool, because it had a 365. This is one of, I'm not sure, one of the 10 on the previous day. Okay, so looking at 40 Erdani. And I got this strange 009990 after the 365 for those two integers. You can go to this online calculator, this arbitrary precision calculator on the web, plug in these numbers. You go comma 550, comma 550 after n. It'll convert this to 550 digits, and then do the math to 550 digits and post it online in the window. I also use it in my code. I use the good math libraries. And I use my code to search with up to about 350 digits. But that isn't what this is. I can use both to check against each other to make sure the math is right. So this is kind of interesting. It's got the 73s and 88s. It's got the same problem. This is the 50-digit line right here. And it's got all of these numbers here, which is, if I'm thinking about this correctly, these lengths of these lines, of these numbers, should all be greater than 50, or less than 50, but they should average around 50, bounce back and forth, like noise, okay, if this was noise level. And then the other weird thing is that the 3 longest ones are all 45 digits long. That's kind of weird. And then there's this strange, after the third 73, the first 6 digits of pi appear. Okay? Which who knows what that is? What's causing that? I don't know. And it turns out pi has a late 7 and a late 0 in its digits. This is pi. And it turns out the digit after the 7, 3, and 8, 8 doesn't have any of those digits. There's no 0 and 7 in there. I don't know if that means anything, but I thought it was kind of interesting. So this was kind of weird. And I do probabilities to try to say, well, what's the chance of this? But there's one very important thing. I've learned this from the astronomers. If you use probability to calculate whether or not something might be this or that, you've got to be extremely careful, because there are so many explanations that, that I haven't thought of, that if I only think of one, but there turned out to be about 1,000 possibilities. You have to multiply the probabilities by 1,000 if there's 1,000 interesting things that I could have come up with. So if I looked at this, and all the numbers had been greater than 50, I would have gone, oh, that's interesting. Okay, the probability I calculated, I got to multiply by 2. It's not that low probability. It's always you have to multiply it by the number of things that you would find to be interesting, which means that the probability of calculating this, in this case this point was 3, is probably not as good as what I'm thinking. But then it's got these 45 in there. So there may be to this, but it sure looks kind of weird, especially with that pi thrown in there. So this is another one that's kind of fascinating. Another one of the 365s. This one was kind of weird because it turned out the numerator on this turns out to factor to 3 times 7 times 223. And I saw this repeat of the 223 squared. And I thought, I wonder if 223 means anything. So I went to Wikipedia and I looked up the habitable zone of 40 Erdani A. And in Wikipedia it said 223 days is the center of the habitable zone. Okay? So one might speculate, but I'm not going to do it, that this happens to be their day. Right? But it had a 73 with only 1 digit, then 2 digits, until the next 73. And then it had a lot of digits. Right? But then there was another 365 right here. Probability, that was kind of weird. I calculated the probability of this 365, and I got that weird number with all those ones in it. I don't know what's up with that. That just happens. We all know this, because when we look at long strings, you see these long strings of all the same digits sometimes. It's just kind of weird. So by the way, on the habitable zone on 223, it turns out that 40 Erdani star system was used in Star Trek for the host star of Vulcan. I found this out like a year after I'd been looking at 40 Erdani a lot. So when people ask, what do? I search for signals from Vulcans. They're not kidding. So, okay. So now this one was kind of weird. This is another one of the 40-foot observations, and this one was a 0.365 ratio. I looked for that too. I looked for 36.5 also. And this one's weird because the 73s and 88s, but the 73s are all contained inside of odd numbers. See how there's this long section of odds, odds. Only in the 73s, which of course themselves are odds. The 88s, they look like they're contained within random numbers. Well, the reason why I kind of noticed this kind of thing is that every now and then I'm looking through the output of the decoder, and I see long strings of even numbers or long strings of odd numbers. And so one of the crazy ideas is that, well, maybe it's being encoded in strings of digits. You can imagine how somebody would create a message from this. Because what they would do is look at the 2 integers and then say, oh, let's just program our computer to find the message we want to send and then send the 2 integers. And then this happens to be something that, you know, is encoding something else. But again, no claim, every one of my slides, no claim of detection. There's a thing called the real scale. We measure how possible something is, and this is 0. Okay, let me get to the GBT real quick, but I wanted to show this one. This one was 3.652788, and then it had some 7 3s with a 599, and then a 3652773. After not enough digits to cause this. This is one of 11 of 9,667 triplets that appeared during one of the days using the 40 book. Then, down here, more 8/8s and 7 3s. But that's kind of weird. It would be priority. So 365, priority, love and kisses. 365, namely Earth. High priority, best regards. Not that I'm claiming that, but that's what someone might look at when they see this.
What's the round trip time from here to there?
33 years, 16.6 light years. So they've heard all our, if there's somebody there, they've heard it all. But by the way, I don't claim that is going on.
Have you tried it on a different star?
Yeah, so when I scan the sky across, I look for 365s all over. And then occasionally I'll look at one there and one there and one there. And then I see these when it's pointing, because I've seen 365s that seem, that was my first talk when I came up 2 years ago, because I showed them, it looks like the 365s are kind of concentrated at certain places in the sky. That was one of my first talks.
Well, yeah, let's...
Okay, I'll move on. So this is GBT. So the GBT has some interesting stuff going on. It turns out this one was present in the off 40 Erdani scan. So this is RFI, even though it turns out that the code has a 7.3 and a 365 in it here. And a 73488 and a 73601. So these numbers are they're kind of weird, but there is a signal on this frequency when the antenna pointed in another direction. So I call this RFI. Then this one this is a weird one because the GBT shows 3 tones at 1446.01, 0.02, and 0.04 megahertz. Those 3 tones are not exactly on the harmonics of 0.01, 0.02, 0.04. They're slightly off. This is 28,633 bits and 14,317 bits. It turns out that offset right there produces 1.9999, which happens to be, when you take e to that number, 7.388. I use e, we don't have enough time to explain this, I guess, but I do companding. Does everybody know what compand? You compress and then expand when you want to transmit high dynamic range in a communication system. So I take e to the number right there. So this is 7.388. Then this is another GBT. So this one I searched for 88365. And I saw 3 triplets on the GBT in the 5 minutes that had an 88365 at the beginning of one of the 4 decoder outlets. These are 2 of them, and this is the 3rd one. The third, 88365, has a 365 after the first 365. That's a chance of 1 in 1,000 that it could happen randomly, right? There's a 365 there. And then it's got this weird thing up here with 366, and this other thing, 3665, separated by 1s, which I think that's kind of weird. And then this was a search for 737373 on the GBT data. And when I found one of the 737373s, there were 14 of them that had this, and one of them had a 7365 in it. In between here and here. Another number I look for. This frequency wasn't seen in the off scan. And this one is suspected to be RFI because you see all those frequencies over there. And then, I think, is this the last slide? No, I'll go 2 slides, I think. Okay. So this one, it turns out the 2 integers, when you divide them, produce this. It's kind of weird. 73,000, 73,000. So it turns out just by chance the remainders of the 2 integers used, and this is pretty reasonable signal to noise ratios. These were pretty high. At this frequency, produce that. Okay, and I don't have time to go into this particular one. Is a little bit different than the others because of these zeros right here. So I'd have to explain what that means. But, and then I think this might be, yeah, this is the last one. So let me go with this. This is search for 3657373. And 3 triplets, I found 3 triplets. This is all 3 of them. This one's 36537, has an 888 in it. Okay, that's not too improbable. That'll happen in 1,000 years. This one is kind of weird. It's got the 3657373, but it also has a 7365 in it, like we saw on the other one. That has a chance of happening 1 in 10,000 digits. And a 9 in front of it, but notice this 9736. There's 9736 in front of this one. And there's a 73 really close to 365, 7373. That's the second of the 3 triplets. And this one is the third one. This one has this 365, 7373. And then up here, it's got a 365 on the ratio. So the digits after the decimal point on the ratio for this one has a 365 and then a 366 over there. And then these long strings of digits where there's missing digits. Anyway, so I don't have any conclusions about this. I'm just poking around looking to see what is coming out of this stuff.
You're finding numbers.
Pardon me?
You're finding numbers.
Well, you know, I mean, someone might be able to glean that, like, yeah, maybe if they did want to send us back stuff, that this is stuff that we used to send, and so they're sending us the same stuff, right? But it's too early to say what any of this is, even though the probabilities calculate at ridiculously low numbers, okay? So I'm going to be presenting this in about 2 weeks at the Berkeley SETI Research Center in Berkeley, and see what they have to say. It's entertaining. Okay, thanks a lot.
Thank you, Skip, for a very interesting presentation. Next up is Dr. Rich Russell. And your presentation is on Monte Carlo analysis. Yeah, it looks like we need a break here too. Let's start back in about 7, 8 minutes.
Tell us about the motel too. Yeah. Well, I've been talking about this. It's just kind of,
First one's yes, here. 365. They're fascinated by it. I showed these guys to Duncan Warmer. This is on Wednesday last week. Duncan was the discoverer of the first mass radio. And he happened to be here for StarQuest. And for other things. Yeah, other things. So I would he said, you know, I showed him. So I showed him my contract. With the repeat of the 365, 27. And it was like most of the slides when I showed him. And he laughed at that. Yeah, so he laughed at that. Absolutely. So you can calculate that's what communication is all about, right? Every system is yes. Because they have to know what they're supposed to do. And even though we're doing it, we're going, oh, calculate. No, that's what it is.
Because then he knew that
without some kind of calculation.
That's
that's a signal probability. Communication systems kind of. So it's 10%. Don't calculate. That's how it's squelching on.
I mean, I think
It's squelching on like a radio. It's just all it is. It's a threshold. It says the probability is going to be considered
but then,
yes, exactly. Yeah, they look at all of the high end to avoid false.
that's quantum.
Yeah, so that's, you know, in communication,
Yeah, you didn't see that in the SARA.
well, these started showing up when I was doing scientific.
Yeah, different SARA.
I have connected noise to the system. I've connected actual random noise. Digital noise. Look, does it show up? I did. Yes, of course it shows up. It shows up right with the probability you would calculate.
What about?
Not the 1 in 100,000. So that'll be pretty much the same. It's also scanned, yeah. So that's why I always, you know, got to ask this. Scan across the sky, scan minus 7.6 definition under rating. So I'm looking at all the stuff. But here's the problem with those guys up there. And when I'm pointing over there, I can see stuff and say, oh, it's not like system. But they're just kind of so the problem with using star is that we don't know the density until it's civilization. Total speculation. Well, they may not be, but they may have already communicated with each other, they're close to each other, to us. They can say, so they can call their data 365 and 7. But maybe the 223 is different. Maybe 223 is their data. Who knows? It's total speculation.
There's some repetition of other stars, but not.
Well, in other, the only other one I found here is Park's 11,000. And Park's 11,000 has some really crazy numbers. Right? It's so crazy. I was wondering here, I have a way here.
How far away is that?
That one was, I think, 7 meters. I'm not sure. Don't quote me on that.
How about between 40 or
Oh, they're like way I believe they're way
to each other?
I think so. I think they're like
What is the ratio?
That will get a code test, so that's really hard. You know, the one thing I didn't get a chance to say is I couldn't talk for another hour. But I do want to say is that's right. If you don't want to call up, somebody is that.
So that should be out for
Unless the industry's transmitting all the that means our FFT has a size. As the transmitter.
Yeah. Like
what are the chances of that?
Nice.
0. Okay?
Why is it can be included in the video? They can't. They're not professionals.
Those are the tools. Yes, they're called philoscopes. They said it's they were told to they look at it and say, well,
okay, but I didn't get what the guy dropped.
I'll be picking up more.
Yeah.
Have that.
Yeah. Well, and even it's our kind of demand. They would say 88 instead of 73. Not uncommon. This is worse here and here. But oh, it's a matter of communicating with each other. 78 instead of 73. So that's but let me just finish on that real quick. Is the clocks have to agree between there and here. And the FFT size has to be the same line. Because this does not work if the integers are not correct. So if for some reason it was just off one bit, or it was a ratio of things, and I ended up with 2:22, and it was actually transmitted as 2:1, then the 2 is approximately half of that. Then we plug them in, you don't get all these digits. So here's the giant leap, which, again, I don't think it's just regression. Now, if you were hearing a bunch of signals from another planet, it's always exciting. They didn't know you were there. Oh, I know. There's tons of stuff. Oh, it's coming up somewhere around 6.2 megahertz. And it's getting more and more precise every spread out long wavelengths close by, pointing at us. It's going to see 5 megahertz. Getting more and more precise over time. There's only 15 and another 20. So more and more precise. They can learn to understand everything. They don't understand. And in the process say, why don't we align translation inverse? Why don't we build our own and with standard costs from the client? Well, basically, I hope because we're just poking around. I'm just turning over fingers. So I'm just poking around, looking at our work done. So I don't know something, but if somebody were to say that extremely far-fetched, we already know our costs, therefore we want to reduce our costs in their transport. Because the chances of getting, well, you think about it, can I create 350 digital specific 2-minute triggers? Will I know their clocks? The answer is yes. So if we looked at those guys' transmitters, and we guessed, this turns out that the GBT was 3 gigahertz clock.
I don't show
That's
up
divided by 16 and then by 16.
a methodology to explain to them after they pay that bill.
1024 below, 2 to 10 below, 3 gigahertz. Somebody will say, well, let's try 1.5 gigahertz. Let's try 1 gigahertz divided by that. Let's try this. So a whole bunch of triplets in that with all these different clock rates, and we can't tell what they are. They don't have long, they might have the first 6 digits, but then after the first 6 digits, it's all just put out.
How long? And particularly, trending.
Well, again, I don't claim. But that's 16
So this whole
33 years around trip. So they know our standard. If there's something there. So, and you can, if they're interested in like, here's a something they had the habitable zone is 220 days. 40 or 98.
That's one.
But any other evidence?
You look at all those in the tableau.
Oh, stars. No. There's no planets.
If I don't have
Planets have been discovered around. They look too large.
Then, if you think that that's the
Yeah. So when I'm at the that's one we should have had. When I'm at the Berkeley City Research City, and they know me because I'm I'll just come back and forth around. I'll just come back and forth around. But if they say, give me another 40 grand, give me 10 minutes. Here's the problem. These are just all That's what we're good time in terms of it's just like
Hey, everybody. Next up is Dr. Rich Russell, all the way here from Colorado, right?
Colorado, yeah.
And,
All right.
he's talking about Monte Carlo analysis regarding,
Well, just all the math you do on figuring out your Jansky's and figuring out the locations and sources that we got. So this is sort of taking equations and showing how you do multivariable analysis.
okay, great.
So it's a poor man's version of that, so everybody in the room should be able to do it. But first, since Skip gave this pulsar thing, at Deep Space Exploration Society, we actually put a pulsar simulator together because we were trying to figure out, well, how do you test this stuff unless you got some data? So we put a pulsar simulator, this little device here, plugs into the back of your radio in the UHF, VHF slot, doesn't matter. And then the audio output on your SkyPipe, which has a max 10 millisecond sample rate. And so this thing allows you to do full blast pulsars above noise, and then change your pulsar rate. And then these little devices here will allow you to change the pulsar beam width, or pulse width. And then I can attenuate down, this is what it looks like, I think that's 1 sample per second. And all these dropouts are because of SkyPipe. And then we can attenuate the pulsar rate down to below the noise floor. And that's what it looks like. I went from there to the full attenuation, and then that's sort of the zoom in. Of course, these are my dropouts again, right? So we can get it down that low, and if we add more attenuators, we can even get lower. So the goal was, if my software can't pick that up with full blast pulsars, then I can't pick that up. But if I can pick that up, can I also pick that up? Okay, so we have now a pulsar simulator. Now we're going to add in dispersion member, and I think the double pulses we didn't have any clue about before. So I'm going to see if we can get the guys to add that in. So this is really helping out. We can actually play with all the software to check pulsars. And what happens is the SkyPipe, I just take that in an Excel file, and then I run the data. So this is a sort of a quick impromptu thing I'm going to show you. But so my theory here is that it's all repetitive. Noise is greater than pulsar signals. Pulsar signals provide a slight increase in signal greater than background noise over time. And then you take a large number of bins and So I've got a bunch of little rules there. This is sort of the basis. I bin these things, and then I subtract the lowest number out of here, which would be the noise. Because you're theoretically the highest number. You have a little, the bin with the pulsar in it is never the lowest number over time. So you always take the lowest number out. And then you take all these bins and then you subtract the lowest number from all the bins. And what you'll do is you'll get these little bars that'll start growing on you, like stalactites. So I did it, here's the loud, slow and loud. And then I just took standard deviation of the difference between these two, and I took how many bins did I get above a certain standard deviation, and that gives me 2, and then it gives me a quick, what's the time between those bins. So I get 2 there, and then this is my slow and quiet, which you saw there, and I also got two bins up, okay? And the bin differences are basically how many bins you got across and your sample rates and all that kind of stuff. So you basically tell what the difference between those two are. Big picture is I was able to detect something I knew about and then when it dropped the noise, I was able to also get it. Okay? Now, it doesn't mean this is great Pulsar software, this is Excel. But once I got the model built, I think I can go and sort of program it now. But I can also test out anybody else's Pulsar programs that you've got. You send me a data file, I'll run it, or actually I can produce a data file for you and let you go run your Pulsar software against it, 100,000 pulses, things like that. So I was able to make 30,000, 10 minutes I make 30,000 samples, which is great data source. And we can speed it up and all that kind of stuff. So I just want to let you know that we can simulate pulsars now and get data for it. And that's what we're doing over at the club. Because pulsars are our next big thing over at what we're doing. Okay, I'm in the Deep Space Exploration Society. We're a Colorado-based, Colorado Springs-based group that has inherited a 60-foot dish in the middle of a cornfield in Haswell, Colorado, which is sort of closer to Kansas than anything else. This thing, here is the cornfields. This is our property. We have 17 acres. We own 5 of that. There's a bunker right there. There's the road coming in. And this is my drone. Flying over the drone and taking pictures of this thing. We've got a little camera in there. So we've inherited this thing. All the copper was stripped when we first got it. That everybody, is an Army asset, and it was sitting out there for 30 years. And all the copper was stripped. There's a 20-foot bunker down there, and the only access we had to that thing was a shaft. And when the guy went down the shaft, he landed on a dead carcass of a cow. I mean, that's the start of the whole, that's our adventure. I consider us the gold rush of radio astronomy. The guys went down there, all this land here, they said, you gotta wear boots because they got rattlesnakes out there. So this is me, 2 years ago when they introduced me to this place, that I'm wearing my boots, long, everything like that, and guys are walking around with sticks to make sure that they can move the rattlesnakes out of the way. I've never seen a rattlesnake, by the way, when I've been down there, but that's a good myth for the new guys. So I got 2 papers in. We had 2 papers before. One of the key things we're doing in the society is thou shalt write papers and document the results. What we got is a bunch of radio engineers, mechanics, everybody, and they've never really documented what they're doing. So when I came in, I said, we're going to document this. We're going to start writing papers. So we've had 6 papers so far in the last 2 years out of the group, and we're going to continue that. And everything from solar power, we're fully off the grid, no power, no water, no nothing. We put our own propane generator in, and so that's what we're going to do. Okay, so here's our site. This is our site outside the group. They used to, in the 1972, they used to have a large tower here. This is what happens when you sell a 60-foot dish, government property for sale. I think the guy who bought it, $5,000 for 17 acres and a 60-foot dish in a bunker. Right? So, and this is Paul Blishner. That's why we named it after him. He's still alive. And so this used to be a tropospheric radio propagation studies site. They were trying to figure out how much. They used to have a 500-foot tower, I think that's that. And my understanding is they actually had to dynamite it and let it fall over because they couldn't figure out how to dismantle it. But that's our 6-foot dish, and then that's the 500-foot tower. No longer there, but the mounts are still there. So tropospheric radio propagation, we're also going to do, our plan on doing moon mounts and tropospheric radio, because I got a bunch of hams in there, and I got a couple radio astronomers, and I got guys who just like to do infrastructure stuff. So to get the ham guys staying involved, we got a full ham. K0 PRT is our club station, but we use a 60-foot dish. We got all the other antennas there too. So we're gonna do moon mounts, tropospheric, meteor scatter, everything we can think of. This site should be able to do, and we're going to be a pretty good moon bounce base with a 60-foot dish. Okay, here's what it looks like when a ramp sits in the middle of a field for a long period of time. That's the same. And we just said, actually, they just, this last 2 weeks, they put fencing up there to try to keep this is our number one thing. We had to go dig in there to get to the door. And that's one of our standard things. This is the bunker. Pretty good bunker down there. And there's about 2 feet of dirt above the top of that. And it stays cool the whole year. It stays a really good temperature. Problem is, it's too far from the dish to put all my electronics in there. So we have a comm band, and that comm band gets to 160 degrees, and we melted our Wi-Fi connection the other day. It's not really good for stable temperature receiving. So the guys are working on that. We don't have any power to keep air conditioning up in there. So we're running on railroad batteries and solar power. Okay, that's our comm band. It's an old NOAA comm band. We got all sorts of antennas for everything else in there. There's some of our solar power, battery compartment there. And this is all your fully constructed now. We put in from scratch, put in a propane generator and propane tanks and all that kind of stuff. So the guys have actually installed all the infrastructure. They had no power, no nothing. And our problem with getting power is we don't have enough funding to pay monthly bills. So we're just not going to get power. All right. Everybody has $30,000 to give us power. Think about it. All right, here's sort of the specs on the dish. And I'll just let you look at that thing. About 42.5 dBi gain on this thing, 60-foot dish. We just got our full 3 axis control, and we got our our tracking system working. So now we can just dial in, write ascension declination, say go, and it goes, and it'll track it. So that's just been up in the last month. This is our 4-band feed that we just now got installed, VHF, UHF, 1296 and 1420 helixes. So this thing is now feeding going right down to our comm band, and then we're going to put our receivers. So Mike is going to loan me a Raspberry, and then I think I got Skip to come and bring some of the back end stuff. Yeah.
Do you have LNAs on those?
Say again?
Do you have LNAs on those?
Preamps. Yeah, they got preamps in them. They're switchable too. This is a 2-way. This is so I can transmit moon balance. So I got 2-way. I've got a radio astronomy mode which runs all the time, and then if I want to transmit, I've got 4 transmit systems down at the different frequencies, and I can run moon balance 420 troposphere off that feed. And then normal mode, we keep it in radio astronomy mode, which is receive only. But I think about 40 dBi gain. So it has to go down about 120 feet down to the comm band. So,
I noticed you had stands. What do you call it? Go back a slide, please. Yeah, over on the bottom right corner.
Right.
Is that permanent?
Yeah, that's permanent.
Okay.
So yeah, we get up here on the feed. Right here, you just lay this thing down, and that's where you're standing right here. This is Greg O'Brien who invented that. We got a couple of papers on that. In fact, the microwave conference, we have a full paper on that guy, specs on that. So basically, he puts these things in, we can mount it on the feed, and then actually got a cable going directly down. So it's primary focus antenna. So the feed's here, and then we basically run the cable straight down, and then down here, and then down down here.
Is the dish set up for tracking?
Yeah. Yeah, full ASL. So this is our club station. So this was actually taken by a bunch of interlopers who decided to get on our property and take a nice picture there, so we convinced them that if they give us the rights to the picture, then we'll invite them to everything, and they can take pictures all day long. So they're very happy. They're very, as part of trespassers taking pictures on our land, now they're full members of our photography team. We're very happy with that. Actually, this is Denver, Colorado Springs, and Pueblo. Okay. So that's, by the way, this was during one of the meteor showers, so you got some meteors there too. So anybody wants to get these guys to take your pictures, that's their site there. This is the inside of our command. This is when we put air conditioning in there, but when nobody's there, we're just running hot, just like an oven. Our primary thing is we've got all the power. There's a little thing I didn't show it in detail, but we've got all the power right here of all the batteries and everything, so we can remotely watch it. We got, we use this laptop as our primary. There's a Spectre Cipher there. Our primary communications remotely is this. The guy put power in his granddaughter, gave him this camera, and that's looking at that, and we do the Wi-Fi connection to that little camera. So a pink camera is our total thing. We keep kidding him about it, but it's working great, yeah.
Was the dish in mechanically reasonable condition?
The guys had to go in and redo all the gears. Well, not, excuse me, they did have to they had to re-grease them, and they had to clean them up and all that kind of stuff. But yeah, no, absolutely. The gearing was good. The power, the controllers, and all the copper cables were gone.
But were there motors there?
Yeah.
And did you have to refurbish the motors?
I don't know how much they did, but I'll tell you what, it took 7 years to get up to this, to where it is now. And I like to say that I don't know how to do mechanical stuff. There's guys there that did all this mechanical stuff over 7 years, got this whole site infrastructure working, and now we're just at the point where we can start doing science with it. We're just there. I mean, this week they put that feedback in because one of the relays was causing jittery data. On our first set of data we took a month ago, that feed, the data was jittery because there was a relay in the relay in there that was arcing over or something. So we just replaced, while I'm here, they're replacing the feed, actually yesterday. And I can go team viewer and I can look at all the data, remotely pull data off, and we'll do drift scans. But when we're down there, we can do full tracking and everything like that.
How do you do your internet connection?
You got a cell phone tower that's about 10 miles away that we can hit, and so yeah, we got some network guys in there. We keep inheriting guys. We got a network guy in there who's going to take our cell phone and network it all out. So this is the perfect place for guys who have a skill but don't know how to apply it to radio astronomy, and they go in there and there's a million jobs. And you guys just want to take a break, come down there and apply one of your skills. We'll point you. So it's a real good group. We meet twice a month. I have a science meeting, and then we have an engineering meeting. Our science meeting is trying to get these guys to, why are you doing this? And what are the data products we're trying to get? And then the engineers, 2 weeks later, come up with, now, to get that, we sort of need to go build this. And then those guys go off and build stuff. So it's a very cohesive group, and we've got a lot of guys playing. Okay, so I'm new to radio astronomy. This is my third career. Retired Navy submariner, space guy, defense contractor for 20 years, and I retired from that. And so I said, well, what can I do to keep me from driving my wife crazy? Well, I don't know anything about radio astronomy or astrophysics, so I'm going to be an amateur astrophysicist. Okay, that's my job. So it doesn't pay anything. It's like negative. So this is part of my learning the math. Okay, what can I do to make me understand the math? One of the things I did in my defense contracting stuff was to take large sets of data and use Monte Carlo to analyze multiple variables. So you got a little equation there and it has one variable in it. That's relatively straightforward. But when you have to start figuring out ranges between multiple equations, and then each variable has ranges to them. For example, you guys are doing measurements, and you can say hey, your noise source is between 0.1 dB and 0.3 dB. But then you cascade that against all this other equipment, and that also has ranges. This will allow you to put all those ranges in and put a model for your system together, and then say, okay, here's where the probability your sweet spots are. Okay, so that's the purpose of Monte Carlo. It's purely a technique, and I'm going to give you all the code. You guys can put this in your Excel and run Monte Carlo programs, and basically all you have to do is put your model in there in some kind of a formula, and then this will run your graphs and everything. Okay, so I think I said all that. So it's multiple variables. What I did here to test this out, there's the NRAO course has one of the problems there was can you detect Mars? You know, and it's simply when the sun hits Mars and then it reflects back to the Earth. Can we detect Mars? What is the ranges? So they had a static problem where they said basically here's the distance between Earth and Mars. Here's point numbers. And then you have to just calculate the point numbers. So what I did is I took those formulas and I said, well, Mars really orbits, so it goes between here and here. And then I've got variables in my receiving system, and there's variables in reflectivity, which is how much that light gets reflected. So I'm going to add those to the equations and then run the model. So basically I had a known answer from the course, and then I just added the ranges in the equations, and I came up with some sort of cool stuff. But it's just an example of how to run this. And then so the goal was that if I get this thing sort of to work, and I start understanding how to work it, then I want to model our radio telescope, all of the different variables on the radio telescope, to say, okay, what is the ranges I can detect, both in frequency, amplitudes, all that, to characterize what I'm doing. And so I know if I get something, I know that, yeah, that's in range of the Monte Carlo too. Big picture is, you have to sit there and dimension a bunch of stuff, but I got a loop here where I collect the data from different, I'm going to call them tuples, different bins in the Excel code, and basically each of those equals a variable. I collect it, and then over here I basically deposit the results, okay, in a spreadsheet. So that's all I'm really doing here. And some of these are variables, some of these are actually results, calculations I do. So I'm just collecting it and then I'm depositing it, okay? And I'll explain why I have to do that, but, okay, so these are the equations I used in the calculations. So they got volumetric luminosity, they got temperature of Mars, reflectivity change. Reflectivity is how much light is actually getting beamed off. So you got, Mars is so far away from the sun, so you got this radius here from the sun, and then you got luminosity of the sun, and then this is what Mars is, but now Mars can change that based if I've got a Mars sandstorm or something like that, and I get less reflectivity, and I don't see it as bright, so there's a range on reflectivity of how much it actually comes back to the Earth. And then you got this whole equation that's actually in the, I didn't make this up, based on what's the arc seconds of Mars, and then what is the signal strength in Jansky's of Mars. That's the equation they use there. So basically, these sort of cascaded equations, I need that one to get to this, etc. And you can see how you can start thinking, well, I've got the range of Mars here, and a range of and I got a range of Mars to Earth, is RM, and then I've got all these other variables that I can range based on where Mars is in the orbit and all that kind of stuff any time of the day. So I did that. The way you sort of set that up is you set up all your variables. I call this my control panel. Here's your variables. And then I put a min and a max, so this is your range. You select. And then this is a random number generator. What it does is it takes that and then it adds the difference between the two. And it'll come up with a random number generator, a random number between these two numbers, including those two numbers. Here's your watch unit. So fundamentally is every time this thing cycles in a loop, this number changes. And then when this number changes, that gets fed into the equation. So now over like 500 samples, I'm continuously changing the inputs to my numbers. And I'm collecting them each loop. Okay, this is a quick example of how it looks. Here's the distance from Mars, here's the frequency, so I can change the frequencies. And then, one of the major things I did was just the number of AUs, which is the distance between Earth and the Sun. And, where's that in Mars? And then here's the Mars reflectivity, and then it just goes on and down. So those are sort of the results column. So when I told you that this thing is depositing the results, this is it. And then what you do is you take that total results list you just did, and you use what's called the percentile. Percentile is, when you have 100%, that means that all the data is, say for that's 0.542, all the data is, let me get a better number here, 5.85 is the signal strength of Mars there. 100% of all the data is below that number. Okay? So here is, I can say, at this distance, 0.542 AU, that is gives you the maximum signal strength that we can see in Mars. Okay? And that's the Mars-Earth distance. And then that's at 15 gigahertz with a reflectivity of 0. That gives you the max signal strength. But then that point is 0%. Well, obviously, I'm way down here. 50%. So 50% of the time, though, I can detect something at 2.1, but I'm going down to 0.14 Janskys with a 5.2% reflectivity. All right, and the frequency I get down to 7.5 gigahertz. Okay, so it tells me that maybe I can pick something up if I can get my sensitivity down. I can get my sensitivity to get that number of Janskys. So I can actually see if the equipment can detect the source based on all the possible ranges of the source. So that's the goal here. So Mars had a lot of variability based on that, and big picture is 1.542 AU. Mars, then when it gets over here, it's 2.542, and the closest distance here is 0.524 AU from this Earth. But when Mars is over here, well, I can't see it anyway because of that, so somewhere over here might be the largest distance Mars is, but I can actually see the conclusions. Okay, some quick examples here. So first you do is you take, I'm only going to change one variable, so I keep all these guys the same, and I change one variable. Here I think I arranged it from the minimum to I think 3.542. So this is just the difference at the Mars Earth distance of 0.542 AU. Here's what the Jansky number of what we're getting for Mars. But as you go in distance, so we're rotating around the sun, Mars is offset from the Earth, you can see how fast the distance goes down. That's just changing one variable at a time. The other ones was, what if I change? Okay, so I'm now going to do multiples. So I'm going to change the frequency from 14.2 142 megahertz to 115 gigahertz, and then I change my Mars distance, and then I change my reflectivity. I get this spread. All right, so somewhere in here is I'm getting the different Jansky levels going down. But I still got that one peak there, but now I've got this range that I didn't have before. So now I've got all these guys changing. And by the way, you get this thing in tabular, and you get it. I just plotted it. This is an example of, obviously, Jansky's over here again. This is what happens in frequency. I just changed frequency. This is what happens if I just change randomly reflectivity. So it's all over the map on reflectivity there. Okay, so how we're going to apply this, got the 60-foot dish, and I had this thing set backwards, so I was going to brief this last. tomorrow, but basically we're, multi-band feed. Oh, I know what I was going to, what I was explaining this is now, if I take the equations of this equation here, which basically tells me what is my sensitivity of my dish and my receivers, then I plug those numbers in and I put another control panel with the variables in there, and I say, okay, what are my variables on my receiving system? And he's using these standard equations to do that. Then, and I change the ranges on here. So here is I'm changing my bandwidth, and I get, you know, that delta there for bandwidth against, this is bandwidth in this direction, and that's my receiving sensitivity in Jansky's. And then I change integration time. This is what integration time does to me. If I change both of them, I can get a very, you know, what's my best view is, you know, between bandwidth and Jansky's. Then if I change multiple variables here, you know, I get the same kind of plot here. So this big picture is I can do, here's my source, my best output of my source. That would be the closest distance. I have to be 15 gigahertz, zero reflectivity, and I get about 5.52 Jansky's as my source. And here I have to be at the highest bandwidth I got there, and I can receive that, but anything less, I'm not really, I'm sorry, I have to be down, 72 is bad. Right, so I'm right here, about 4.75. I can detect the highest source, but below that I can't get anything but the highest source. So the guy has to be the closest, and everything has to be perfect at 15 gigahertz. But the best I can pick up is down here, and it's even the wrong, you know, with this kind of bandwidth. So where am I going with that? The big picture is you can tell that, I can immediately tell that source where the source has to be, what parameters the source has to be at, and what parameters I have to be at in order to detect both of them. That makes sense? Makes sense, you guys? So I'm doing both, and then I'm going to plot both. Yeah.
Are you actually going to try this at like 15 gigahertz?
Well, I don't have a 15 gigahertz feed right now. So what I was trying to do is I actually arranged this thing to go down. I put the source at a lower frequency. And so if you look at my frequencies down here, I was trying to get the frequencies I'm capable of doing, but they're down here. But that gives me this source strength.
Yeah.
But I can't get down to that source strength at those frequencies with my dish. All right? So I cannot see Mars. That's the bottom line. The 60-foot dish, my equipment. Right? But I can see Mars if I'm at 15 gigahertz and it's the closest approach. Right? That's what this is telling me, and I'm just using the equations and the spreads. So now what I really want to do is, this is a quick rough estimate of my radio telescope. I can actually put the model for my radio telescope with the gains, all the gains and the ranges of the gains at different frequencies, and I can actually model the receiving setup in the dish properly, and then I can see the spread on that. Even what's the temperature, outside temperature, inside temperature of each of those, and what their performance is. I can model that with Monte Carlo. And then I can tell you that, yeah, you have to be in the dead of winter at 0 degrees in the comm band to get enough sensitivity to pick this thing up. All right, that's probably my only way I'm going to see this thing. But that's the kind of stuff I think we can do. Yeah?
Are you doing this in the spirit of the moon bouncers who try to see if they can see the moon with their antenna by allowing it to scan?
I am one of those who has a 31 element, 430 megahertz thing, trying to pick up moon bounce with no possibility of doing that in my head. Mathematically, there's no possibility of doing that, but you can't tell me that. I know it's going to be there. I know I
You're doing what they do in the moon bouncers do. They go to the VK3MO website, right? You can put all the...
I have VK3UM on my
Okay, right, okay. So, but you're doing it in a way to vary all the variables and find walk over to the optimal place.
So if you take that, when you're talking about VK3UM has a calculator, right? But what you have to do there is you have to pick the numbers and then it comes up with an answer. So my biggest dilemma is I don't know what numbers to pick. So I'm going to pick the ranges of everything I know. And I'm going to say, now run all those ranges, and then it tells me which combination should meet the criteria. And then I either have that capability to do those combinations or I don't. That I think is the difference, is I will take any equation and plug it in here and then run ranges against them all day long. Yeah?
Why do we use volumetric luminosity?
Because it was in the calculation. Okay, I'm taking.
Instead of.
I gotta get the sun. Sun's shining on Mars. Mars has a certain angular size, stuff like that. And that gives me luminosity.
But it's luminosity for entire frequencies.
Well, no. It's luminosity for that. Well, that's what I'm saying. It's luminosity. That's the equation.
Yes, but
right.
you use volumetric luminosity instead of particular frequency luminosity.
Well, that has temperature. What I do for temperature here is we have a frequency in here. There's my frequency calculation right there.
Yeah, but I understand, but
you're saying right here.
It's not that I have no clue, but the question is why volumetric?
What's happening is that the sunlight is heating up Mars to a certain temperature, and it's the volumetric luminosity that's heating it.
Yeah, so is
Now it's the black body temperature from Mars that you're detecting.
So what do you use as the black body temperature of Mars?
Right, yeah.
Well, what do I use? What do I do?
So, but if
I used what was in the example. I'm sorry. I think I did. I think I just plugged that in.
I think he's using the black body and reflected.
Let's see. Well, see, I think I plugged their number in.
That's not the right thing.
Oh, I'm sorry. Sun temperature.
When you do it with the moon,
I'm sorry. I did. Guys, I used their sun temperature here.
Yeah, so you're assuming that it's reflected sunlight. People who use the moon assume that it's the black body radiation temperature of the moon, which most people say is 200 Kelvin.
Okay, so this is what I have the example, Brandon. It basically told me the number of sun temperature here. So here I can vary the sun temperature in the model because I built it in, but I did for this example. I just used 1500 degrees Kelvin, and that's the T4 in the calculation.
So now that's really interesting because I don't know the answer to this question, whether or not I'm likely to see it radiating as a black body or see it in reflected sunlight. You could study both.
I can vary a bunch of stuff here. And I don't even know that question to be able to say that my model works that way, but maybe you can use my model because you know why to change these things.
Right.
I'll just put his calculations in, and so I find that the NRAO examples with all the equations in them is perfect for this kind of analysis. They actually walk you through a single variable. They actually pick a point and they walk you through all the math on it to come up with the answers. And I'm just plugging that into the models. All right? It doesn't mean I actually know what I'm doing when I'm plugging them in. I'm just doing the mechanics. But guys like that actually may know what the answers look like.
Yeah.
Okay, so where was I going with this thing?
And the temperature of Mars gets.
Well, sort of the end result.
You really lose.
The end result was that I had one point out here where I had enough. This is actually flux down here. This is my percentile. So that I had one point where in the Mars orbit with zero reflectivity and all the other bells and whistles lined up, where I had enough Janskys here that it actually met my, I had the criteria where I can actually see it. This is actually, if everything lined up right, I can get down to 2 Janskys of being able to detect 2 Janskys in my system, and yet the only thing that goes above 2 Janskys is my worst case source number, right? So that's how that's what sort of the answer looks like, all right? And now that's just one example of many things. So now I'm sort of looking for what is my other capability You know, can I model the 40-foot dish for skip and things like that, you know, but give me the formulas and then I can go run these for you. Anyway, it's a quick and dirty, everybody can do it, you just plug that stuff in. You have to be the BBA or the development mode and plug it in as a BBA script. That the stuff I had in the front, and then you're done. Runs pretty good. You have to be in macro to turn on your virus detection. Has to. Okay, in summary, multivariable models. Let's see, determine range. The question is, you have to determine ranges of each of your variables. You have to sort of start picking that stuff, and then we're going to start doing this to characterize the listener radio telescope systems and see what that looks like. Okay. More questions? Yeah.
The ranges in your, the values you pick within your ranges, just a uniform probability, equal likelihood of picking any number within that range.
Yeah, that's I use the RND double script there, which is gives me a uniform distribution between 0 and 1. And every sample, it picks between the two, including 0 and 1. So it'll do a uniform distribution. Yes. It's not normal distribution.
Sorry.
Yeah, no,
At the beginning, you said bin size. If you change the bin size, anything change?
I changed the what size?
The bin size.
Oh, yeah, you got my pulsar stuff.
Yeah, right.
Oh, well, yeah. In the way I've got the Excel model set up in that is that I've got a sample. 10 millisecond sample rate. I think SkyPipe does 10 milliseconds, at least with my combination of my computer stuff. So each bin, if I do 10 bins, I've got 0.1 milliseconds, or excuse me, 100 milliseconds of sample time. So if the pulsar is less than 100 milliseconds, I'll have one showing up in there. So, but the problem is I need depth of bins because I need to take averages and mins, subtract minimums to get rid of the noise level. So I need to have depth as well as numbers of bins. So, so I can knock those down to come up with that. But I think I need at least 3 in depth because I want to take the highest number of each, and then I want to subtract the lowest sample. So I'm trying to get rid of the noise, what I think is really the noise sample. But I used 20 down depth, and then I used 10 across. So it gave me, I got 2 peaks within that, you know, that bin size, that depth of bin. But that I sort of set that up manually, and I only did about 20. I got about 300 samples. I was able to do out of 300 samples, even though I had 30,000 samples using my pulsar simulator. I had tons of samples now of anything I wanted. Stuff I saw found online just gave me a couple of minutes of samples, which wasn't enough to prove that I could do it. So now I can make 100,000 samples of anything I want. So that's why we built the simulator, to start doing that stuff. Okay, that's all I got.
This year, I think you may have heard that we're having a total eclipse across the United States.
We are?
I didn't get about this. So, Bill Scott will be talking about a project to observe effects on VLF propagation during the eclipse.
Greetings all. So yes, this is about the upcoming eclipse. I'm Bill and George Lemaster. Hi George. Say hi to him. So he's also here so you can ask him questions about it. And we're doing this along with George Mason, University of Massachusetts, and as you soon find out, many other folks. So as you know, there's an eclipse coming up, so I'm not going to talk much about that. The outline is, some background, some historical stuff, what we're trying to do,
and the conclusion. So imagine that most of you have seen this map. So this is a very interesting display because it's totally wrong for what I care about. That path is the path of visual totality on the Earth. It is not the path of how the ionosphere gets disrupted by the solar eclipse. Because if you think about it, sun, moon, Earth comes down there, that's visual. But at 70 kilometers up or so is the D layer. Beneath the D layer is what I care about. That's actually south of that. Since the E layer is higher than the D layer, the path of totality is south of that. And since the F layer is even higher from the Earth, the F layer's totality is south of that. So this is just for visual, it's not how the ionosphere gets affected. So there's totality for visual and for the shadow. Notice that the shadow hits all of North America, Central America, parts of South America, Hawaii. I care about all of that area, not just the path for the visual totality, but where the shadow is, because that's where it appears as night. So I'm going to go back in history. The first person to ask the question of, hey, does somehow a solar eclipse impact on radio wave propagation was William Eccles. Some of you may know him as a good scientist, some of you may know him as a former president of the Radio Society of Great Britain, but he's probably most famous for is the co-inventor of some device called flip-flop. I understand that device is important in the world, I have no idea why. But anyway, he asked the question, and so he built a receiver at 5,500 meters, kind of low, right? He built it there because Marconi had a transmitter at that frequency that he hoped he could use. Problem is, back in 1912, how much radio communication was going on, folks? Yeah, was that transmitter always on? Nah. So, what he recorded was clicks, scratching noise, strays as he called them, and it got published in Nature. Doesn't quite make the threshold of Nature today. But in 1912, this was the first report that came out on eclipse, and we have no idea what those atmospheric noises actually were, what direction they were coming from, or anything. This is his plot. There's no scale on this because he's just listening with the headphones and says, ah, that one sounds louder. Okay? Like I said, doesn't make the threshold today from Nature, right? But those two humps, that's still of interest today. Why were those humps there? What is going on with them? Okay. Well, right after he did it, on April 17th, some other folks did it. They used a transmitter that was the base, or the support for the antenna, was something called the Eiffel Tower. I don't know if you folks know, but this is an aside. The Eiffel Tower was scheduled for deconstruction in 1908. It was in fact built so it could be deconstructed. And Eiffel had this idea that if he could show that it was being used for science, it would stay around. And so he made a deal with the French military because there was a new thing called wireless, and maybe they should do some experiments. And that's why we have the Eiffel Tower today, was because of those science experiments. He was able to keep it up long enough. But those aerial wires, long gone. It would have been interesting to see it. Anyway, so these folks did some stuff, you know, out in France, Denmark, also Austria picked it up, and some folks in Germany. Notice very different frequency than what Eccles did, twice the frequency basically, so we can't really compare them. That was the first case where people said, hey, we need to start working together. So based upon this and what Eccles did, they said, we're going to start doing experiments where we can work together. So they decided for the eclipse of 1914. Folks, what happened in 1914? A little World War.
that kind of put the kibosh on doing this teaming, right? So it had a nice path. It would have been a great thing to do, but but they knew that group efforts were the way to go after eclipses because they affected such a large landmass. But what also happened in 1914 was the first theoretical paper published on this. Now, he was wrong, but what do we know about science? That's okay. He got it out, people started discussing it, they looked forward, and now we're still publishing a lot of papers on it. But it all started with this guy, and the wood ionosphere didn't exist then. You may know about this guy. He claims to invent something called radar, called chain hole, that was used in the Battle of Britain. You notice there's no hyphen there? He changed his name to spell with a hyphen after he became knighted. So I used his own spelling from 1926. Okay, another try. We're going to do this as a group, right? Well, now the eclipse that they decided to use is down through South America and Africa. And again, totally different frequency than what the previous ones have been done at. No change. Well, why was there no change? A lot of the transmit-receive pairs were up through Scandinavia to Canada and that. It's outside the shadow, right? But no numerical report, just anecdotal stuff we can't really use. So they said after that, okay, we got to do it better. We know we're on the right path to trying to do this. So, 1925, we get this eclipse over the United States. So Scientific American ran every issue, an article in every issue of the magazine for a year before that eclipse, saying, hey folks, guess what? It's coming. We want you to report on it. 1925. By that time, broadcast radio existed. Started in the early 20s in the United States. Lots of farm communities used it because that's how they knew what the prices were for the wheat, hogs, what the weather was. Broadcast radio has become popular. Over 2,000 reports were received by Scientific American. I think in 1925 to have 2,000 people write it down and send it in, that's probably good reporting. The American Radio Relay League got almost 150 reports. That's great. So I looked through every single one of those issues. That's why I know every issue for a year, they said, it's coming. Then it says, it came, and we got 2,000 reports. And I kept looking. No analysis was ever reported. Why? Errors. They said lots of errors. And like the American Radio Relay League, that got almost 150, they said only 50 of the reports were of use. And considering all the ham bands and the spread, there wasn't enough really for any particular band to use. What was missing in those errors? People forgot to say things like, what is their location? That would be kind of nice, right? They forgot to put down things like what date they were reporting. They hoped it was the day of the eclipse, but they don't know. They didn't put down what time. The broadcast band people said, okay, we heard this radio station during the eclipse. What radio station? Okay? So you can see there was a little bit of a problem. So I'm very happy that 2,000 people did this, but we have a little difficulty. What George and I and some others are trying to do is overcome those difficulties. So there's also this interesting experiment done. In the late 20s, it was well known about the day-night effect. I mean, that had been known since the late 1890s. But by the 20s, they knew, okay, it's ionization by the sun. Great. What's causing the ionization? Is it electromagnetic waves from the sun? Or is it particles from the sun? Non-charged particles. Why non-charged? Because if they were charged, they'd hit the magnetic field lines and go to the poles, right? So these are neutral particles coming out of the sun. They didn't know. So Appleton formed a little experiment. This is before he got his Nobel Prize. Says, okay, the moon gets in the way and it stops both the particles and electromagnetic waves. So, well, the particles are still going to take 4 more minutes to get down to Earth. Okay. Well, when the moon gets out of the way, it's coming, both are now coming down. If the ionosphere gets ionized quickly, it's something traveling at the speed of light. If the ionosphere gets ionized much later, it's the particles. So let's see when the ionosphere gets ionized, and we can do that by bouncing signals off of it, and whether they get bounced or not. Really clever experiment because it's using the universe to examine itself. We now take that for granted in the way of doing experiments. It wasn't done much back in those days. Okay, so that's the easy explanation. If you want the full explanation, see me, because in that 4 minutes that those particles are continuing to travel down, that Earth has moved 7,000 kilometers around the sun. So it's a little bit more complex than what I just said. 26 teams around the world took part in this experiment over 3 different solar eclipses. So, really good team effort, over 3 eclipses. Appleton and Chapman, the guy we did this with, in 1935 published a paper on it, and the conclusion of the paper was not which thing did it, but if we're going to do a group study, we ought to agree on how we report the data so everybody reports the data the same way so we can compare it. So here they did it, what we're trying for, right? And that's the conclusion of the paper. So now let me show you some actual studies done with this. Okay, Wolverhampton Grammar School, that's like a high school over here, is about there in England. And France Info is about due south, 600 or so kilometers. So the units here is S units, so it's 6 dB between each of these. See what happens. The eclipse comes, recombination of the D layer becomes absorbed, right? Broadcast band, you don't hear skywave signals during the day because it's absorbed by the D layer of the ionosphere. And then the eclipse ends, gets reionized, and I wish they had taken this out because this, by all theory, has to come back down to this level, okay? But they didn't. Okay, notice the different slopes. What's happening here? I have an electron floating around somewhere up in the D layer. I have an ion floating around someplace up in the D layer, and they have to find each other to recombine. Here, I have the electron on the molecule, it's getting hit with the EM waves from the sun, gets broken off. That's a very characteristic curve of the recombination ionization rates. There's another thing that's interesting about this. Here's where visual totality is. Notice that the receive site and the transmit site are both way south of that. So if you hear that it has to cross the line of totality for the ionosphere to have effect, not true. Anywhere in that shadow line, the D layer gets affected by. Okay, so I'm going to give you another one. This is Radio Luxembourg. Again, received up in the UK. Normal day, can't hear it. It's at 1440 kilohertz. Again, the AM broadcast band. It's a little bit hard to see on this scale, but again, that same 2 slopes, the slower slope going up, more rapid slope coming down is what's happening. Okay? So, you kind of see what happens, folks? You see the shape of those curves? Okay? Tomorrow afternoon, Rich Russell is going to talk about what that's going to be like for the lower frequencies. So I'm not going to go through that stuff. He has a very good presentation on that. So remember this when you hear Rich's talk. Okay, now I'm going to show you what happens at 75 kilohertz. Okay? We're going to go much lower. Here's being received by 5 receive sites. One in England,
1 in the Netherlands, and 3 in Germany. Do they look like the 2 previous charts I showed you? Not even close. They did a really good job to collect this data, and that's where they stopped. They didn't come up with a hypothesis of why it explains this. I have a theory why, but what we're trying to do with this eclipse is actually figure out what's going on here. So, we formed this group called Eclipse Mob, and we're going to have everybody listen to the same transmitter, WWVB, in Fort Collins, Colorado, 60 kilohertz, okay? So we don't have this problem of different people in different locations listening to different stations. Turns out, some of you folks are familiar with Super SID and the Navy's transmitters. The U.S. Navy has 2 transmitters for experimental use located in Dixon, California. That's right outside Sacramento. They've agreed in principle, because I can't force them to do anything, to turn on those 2 transmitters for us. At the time this slide was prepared, it was at 57.5. The frequency's now changed. So 55.5 kilohertz will be turned on. And also 135.95 kilohertz. Some of you may recognize the significance of the last number, 135.95. Ham radio community is about to obtain access to what's known as the 136 band. That transmitter has a more efficient antenna and more kilowatts they can put out than any ham will ever be allowed. And so the steady propagation with that one during this time is going to be great. No guarantee they can be on, because the Navy can't guarantee that, but that's currently the intent. Okay, so the WWVB, you all know it. It's used to set time in watches, clocks, and everything. That's the antenna, that wire vertically right there. Those 4 towers you see, that supports the capacitive top half of it. It's really nice. If you go out there, go visit them. It's a great group of folks. John Lau runs that place. Here's coverage maps of it during day and night. These are coverage maps they assume for being picked up by watch. How big do you think the antenna is in that watch? How sensitive is that receiver? You notice that Washington and Oregon don't have coverage during the day? We have verified for our experiment that we can get this signal on a nice little island out there in Washington, so that we in fact can have coverage before, during, and after the eclipse. Here's what the signal looks like. There's 2, it's an amplitude modulated signal, also BPSK, but I'm only going to talk about the amplitude modulation. This is 0, and also it's steady state. This is a 1, it's down 17 dB. It's 1/7 of this. And as you can see, now it also does BPSK in this, which flips the phase. Okay. So that's what the signal basically looks like. I'm going to show you 3 bits. The end of each bit has the 0 value. That's a 0 from here to here. That's a 1 because it has the low thing. And this is what they call a marker bit. It's 1 bit per second is transmitted. I care about the amplitude. Remember those plots I showed you from 711 kilohertz, 1440, and 75 kilohertz? Those are all amplitude versus time. Folks, how do you want me to compute the amplitude of this signal? I vote for we just do these. There's folks around who do these, also compute the amplitude down here, and then just add 17 dB to it to add it to those. The signal to noise ratio is a little bit worse there, so I don't really like that. There's other folks who just take an average of all this. But since these values are always changing every second, well, I should say every second, every minute, because the time changes, you get averages that jump all around. So I'm just going to do these. If anybody has other opinions of what should be done, please let me know. So we send out a kit. I'm going to pass it around. So this in the box is the receiver kit. But you just want to take it and start passing it. And this is the antenna. Notice it's in a around a plastic tub. All the parts for the kit get mailed to people in this plastic tub. So they use the plastic tub to build it. Okay? This is in fact based upon an antenna done by Tom. So thank you, Tom. That receiver part right there is also Tom designed. He presented both of these at previous SARA conferences. So, folks wrap the antenna. First complaint I heard was, nobody's going to wrap 200 tons of wire. My explanation back to him is, sometimes in science you just have to do work. But there's one more piece that's not on this photo. What do I do with the output of this receiver? The receiver output goes into a smartphone. Why do I want something going into this? This does not care about 60 kilohertz, right? What does this have built into it? Location services. It knows where it is. Date services. Time services. All those problems that we heard about from the previous folks, I can take care of today with this technology. Now, remember, we also had problems with maybe people weren't listening to the same station. What can I also do with this? I take that data in, I can decode WWVB and make sure that's what they're listening to. And I can decode the time off of WWVB and see if it corresponds with the time code that this has to make sure that I'm getting the right signal and nobody's faking out my time. So I need to get the signal from 60 kilohertz down to something that this would take in as its audio input. Audio input usually doesn't go 60 kilohertz. By the way, 2 years ago it did, and they've improved the cell phone so it no longer does that. So what we have is we have basically the antenna based upon Tom's amplifier chip. This chip right here takes an audio tone from the headphone output of the smartphone. And that's a frequency doubler. So I can take, 22 kilohertz, well, 21 kilohertz out. I'm doubling it to 42 kilohertz, okay? This is a mixer. 42 kilohertz, 60 kilohertz. What do I get out? The sum and the difference being 18 kilohertz. So what I feed into the cell phone is an 18 kilohertz signal. I'm also feeding in a bunch of other stuff, but the signal I care about is at 18 kilohertz. So there's an app that goes on this that then takes that all in, packages it up, and ships it up to our web server. So nobody has to send files, fill out forms, all that. It's all being done, okay? I'm trying to solve the problems that existed in all the previous studies, okay? Let's hope I can do that successfully. Okay. So thanks to the National Science Foundation, we got money to do 150 kits. So we're not going to make the 1,000 of Scientific American, which is what I asked National Science Foundation for, but I was glad to get money for 150. But you notice, I got a gap. Last week I was at an IEEE antenna conference in San Diego. Met a professor at North Dakota, so we now have a kid going off there. She knows a EE professor down in South Dakota. So that networking conferences, folks, like this one, sometimes works. So I still won't have a lot, but at least I'm going to have some. The kits were all assembled and put together by the folks at the University of Massachusetts at Boston. Where do you see a lot of kits? And what was my other partner? George Mason University? A few kits there. But folks, if you have a receiver that goes at 60 kilohertz, it doesn't have to be done with this kit. Anything that receives 60 kilohertz, I'm happy with.
So what's the format we want to report it?
Give it to me as a WAV file. I can take just about anything. So, how can you take part in this? Build it on that. All the parts list is on the website. Okay, connected. So if you connect it to a laptop, you folks know about data reporting. You can give me your grid square, if you have, you can give me a zip code, but you can give me some location, date, and time. What we found out is the general public doesn't know about reporting. Okay. I want to know data day before, day after, night before, night after, because I want to know what kind of baseline is. Okay? And then upload the data. Okay. It's all on the website. And by the way, the schematic that I just showed in the presentation is different than the schematic that's in the paper, because we modified it since the paper was put in the proceedings, so go to the website. If anybody's actually interested in building one of these things, I have a few printed circuit boards with me. You're more than welcome to have one. If anybody would like a sticker, I have stickers too. Okay. Now, this is just, so I told you 55.5 and 135. We were able to pick up those signals. So Georgia Tech is also in partnership with us, also being supported by the National Science Foundation. So Georgia Tech system is also looking up at around 300 kilohertz. But I'll show you why Georgia Tech is nice. This system goes from 1 to 450 kilohertz, and they digitize the entire band. So all those Navy transmitters that the Super SID folks get, they're getting. 60 kilohertz, they're getting. Those things up at 300, which is for differential GPS, they're getting. They're getting the whole band for us. Really good time accuracy, good dynamic range, very good sensitivity. It's orthogonal loops, and they're getting relative phase information. All of those kits only collect amplitude data. By knowing relative phase, during daytime, I'm getting the phase of that signal. At night, I'm getting the phase as it also does this. During the eclipse, as it gets darker and darker, the D layer rises in height away from the Earth. That path gets longer, and as it gets longer, that ends up being a phase shift in the received signal. And so I can actually tell how that's moving. So we're taking this data, augmenting with all ours, because these systems are a little bit more expensive. NSF wouldn't pay for 150 of them, but that's going to be a good deal. And that's their current size. Okay. So, as I said, lots of things happened in the past. Yep. Yeah.
Are you familiar with the NCDF beacon system?
Yes.
Are you familiar with the piece of software which follows the height of the reflection?
No.
You walked it.
Okay, so can you tell me about it? Not right now because we got to leave. But
the transmissions are precisely timed.
Right.
The receivers in any PC use multiple time sources to get good time to the PC. And you can actually see the reflection layer, wetness propagation, go up and down. Generally, you see it up and then disappear as a function of time.
Okay, yeah, so let me record. So one of the things we've also got, for those who care about HF, is the sounder at Iowa National Labs, which is on right now 15-minute cadence. I got them to change it to 1-minute cadence. But again, it's a government thing, so.
But here's a sounder system in effect. It's in operation right now with free software to collect it.
Yeah, so I want to get more details from you. Yeah.
Could you, on the schematic, show us what the signal level is coming out of the cell phone, you know, the local oscillator, what would those levels be?
I don't remember, do you?
At least 300 millivolts RMS. At least 300 millivolts RMS out of the phone. The multiplier does require a bit of signal coming into it to do the doubling.
Yeah.
What's the name of the app, and is it for iPhone?
Okay, so it's Eclipse Mom, and there is an iPhone, I have it on mine.
Okay.
But it's in beta release right now, so I can't give it out because Apple has very strict rules on what's done and not done.
Okay.
So as soon as it is released, and instead of testing it today, I'm here, but as soon as it's released, it would be up on the website.
And it'll be called Eclipse Mom?
Yeah.
On the app? Okay.
That's what the beta is called, so I assume that when Apple accepts it, it's called the same thing. It's also for Android.
Okay.
So it's eclipsemob.org is the website. Or you can send an email to info@eclipsemob.org. That goes to a team of people, so somebody will always answer. So while George and I are here, other folks are looking at that. Okay. Any other questions, comments? Okay. Thank you.
All right, Lenny.
Thank you. Thank you. Hey, you didn't come back here.
Oh, yeah. Do we have a laptop up here?
I've shared several times, but there's Everybody, okay, our last presentation before lunch, Wayne will be doing presentation on CubeSat. Thank you, Wayne.
All right, thank you very much, Tom. Well, I'm very happy to be here today presenting a little background and also a proposal on CubeSats that we hope will be of interest to the members of SARA. We presented a similar presentation to this at the Western Conference out in Socorro back in March, and we feel like it was fairly well received. So we wanted to bring it here, of course, and present it to some of the same but a lot of different people in the audience and get feedback on it and so forth. So about a year ago, as a matter of fact, at the last year's Eastern Conference, we started talking about this, and several of us met with Nick Pugh and discussed what they were doing in his part of the world with CubeSats. And since then, I actually was at a conference in Orlando, or RAMS, which is the Reliability and Maintainability Conference, and met Rebecca Austin, who is a PhD candidate up at Vanderbilt. And they have a CubeSat in orbit right now. There's experiment studies radiation effects on semiconductors for satellites in low Earth orbit and so forth. So we've been working with them. So since then, we've evolved this idea of, wow, maybe SARA or some of our group here should form a special interest group of people interested in pursuing radio astronomy in low Earth orbit or above. So that's what we're going to talk about today. My assistant here, by the way, is my son Colin. He did a lot of the background research on CubeSats, what has been done, and so forth. So he's flipping slides today, but go ahead, Colin, next. Okay. A couple of slides on Athens State University. Most of you have seen all this information before, but Athens State is a small university in North Alabama, about 20 miles from Huntsville. We specialize in the upper 2 years, junior and senior years of education, along with several master's degrees programs now. We have about 50 BS degrees, 2 master's degrees. I teach out of the College of Business, but I teach in technology-related areas like management of technology, technology transfer, risk management, statistics, and also aviation management. I've been a pilot for a long time, and I teach our aviation management courses. And that is within the Management of Technology department, and I sort of do all the courses in there. Okay, Colin? We've been coming to SARA conferences now for 3 or 4 years. We have integrated radio astronomy into our MOT program because I found out, and it should come as no surprise, that students of all levels like hands-on activities. It's one thing to read about stuff in textbooks, but if you can put your hand on something, if you can see something work or whatever, then it makes a better impression on you, longer lasting impression. So we've been doing radio astronomy stuff now for several years, and as a matter of fact, the final exam in our risk management class looks like a page out of Dr. Russell's presentation on Monte Carlo analysis here. We'll have to talk about that. But you see some of our stuff, all of our antennas are up in the attic of our 3-story building, so out of sight, out of mind, you know, we don't have people trying to take our antennas down. We have Super SID. You can't see it very well. We have one of Dr. Higgins' Jobe receivers here. We have a lot of legacy stuff. This is a R75, some Icon receivers. We also have Hallicrafters and a Collins R388. All this stuff we play with there. Okay. So what is a CubeSat? Most of you have probably heard of it. CubeSat is a small standardized satellite originally developed by Dr. Bob Twiggs, who is out in California. They've kind of written the book on small educational satellites. I worked with Bob back in the 80s. We launched the first commercial payload from Cape Canaveral Air Force Station, and Bob had one of our payloads. He worked at Weber State College out in Utah at that time. Since then, he has become very world-known, renowned for his work with small satellites. They're cheaper. They're something that can be achieved by the educational community. Next slide, Colin. Typically a 1-unit CubeSat, and I forgot to bring my model up here. Kevin, would you get the little satellite model out of that bag right in front of you there? They're 4 by 4 by 4 inches cube. That is the size of one of them. David's got one too. We sent some of this stuff up to the Dayton area, Hamfest, by the way. But this is the size of a 1-unit CubeSat. I'll pass that around. That just gives you an idea of what we're talking about. That's the minimum size of a CubeSat. The weight is 1.5 kilogram limit, 1.33 I guess it is actually, comes out to about 3 pounds. It has to be self-contained, totally autonomous, such that it doesn't interfere with any of the existing payloads. These little satellites ride piggyback, quote unquote, on existing commercial, some DoD payload launches, and they also eject them from the space station. So a lot of cool stuff going on there. Okay, Colin. Here's a typical CubeSat mission. These little satellites are usually mounted on the payload frustrum or some part of the payload structure that doesn't involve the main payload. And once the main satellite is ejected into orbit, at some point the CubeSats are released or ejected. And their orbit, of course, is totally dependent upon whatever orbit the main payload is seeing. So you basically propose to NASA, even ULA Launch Alliance, the United Launch Alliance in Decatur, Alabama, throw a rock from our university and hit that almost, has opportunities, but you propose an experiment, you get a slot on one of the launch vehicles, you're looking at a 2 or 3 year time frame typically to make this thing happen, and then you have to go away, build, test your satellite, has to meet stringent requirements and so forth. But it also, by the way, a lot of people have been concerned about this potential space debris coming from all these little things. As part of the criteria, you have to have a pre-planned deorbit plan as part of your mission. So most of them come down within a year. Depending on the orbit, they might be up for more than that. Okay, Colin. Okay, so what's been done in the past? Typically, around 100 CubeSats are being launched a year. That number's going up. India, matter of fact, earlier this spring launched 104 CubeSats on one launch. It was a CubeSat dedicated mission, actually. So they squirted out 100 satellites from this one launch. But typically, as you can see, it started out as an educational thing early on, but lately the commercial world has seen the benefits of getting some technology demonstrated in space for a very low cost in a very short amount of time compared to otherwise. Typically, here's the reliability. You can imagine these things are not costing millions of dollars. Some of them maybe cost hundreds of thousands of dollars, but the reliability is not what you might expect from a commercial or a DoD payload. Right now, typically you have 27% in progress. Only 14% of them have achieved their mission. About 20% of them launch into space, never to be heard from again. We don't know what happened to them. They were ejected. 15% of them, we can confirm they failed. Whatever, something went wrong. Some of them are dead on arrival into orbit. They get ejected, they know they were successfully ejected, they just don't respond for whatever reasons. And some of them just, don't get off the ground, so to speak. A lot of people across the country are doing them. This was the 2017 NASA Launch Initiative selections. You can see educational institutions primarily all across the country have proposed and are getting the possibility to ride on a scheduled launch. Vanderbilt in Nashville has, I think, 3 vehicles in progress. One of them is in orbit. 2 of them are about to be launched within the next 6 months to a year. So they've been working on this out of their defense and electronics, space electronics lab there in Nashville. We've visited with them several times. Okay. Okay, so this again just shows some of the things going on. And those of you who are ham operators, most of us I guess, AMSAT of course is very involved in all this. And AMSAT and Vandy have teamed and supporting each other, so to speak. And AMSAT has a series of CubeSats called the Fox series. And the one I mentioned about Vanderbilt, AO85, is in orbit right now. All the information is published on the AMSAT website, and you can actually monitor their data, and there's decoding software and all that available. But again, we're talking about, for a 1 unit CubeSat, about 3 pounds, 4 by 4 by 4 inches in American units, 10 by 10 by 10 centimeters. This is some of the information or the physical buildup of a CubeSat. They actually have some of the same systems you might expect on a regular satellite. They have to have communications, data, upload, download. AMSAT, of course, has on all their satellites a typical ham repeater, 400 megahertz up, 2 meters down, which is a good thing for ham operators. They also have to have some sort of attitude control system. And next slide, Colin. Okay, past and present. One of the slides that I took out of here showed of all the satellites that have been launched, how many of them have been dedicated to radio astronomy. And the reason I took it out is because you can't see the radio astronomy line on the chart. It's so small. There's been probably 1,000 CubeSats launched, maybe a dozen or so at most. Probably less than a dozen have any relationship to radio astronomy. So here's 3 or 4 of them that are either launched or in consideration to be launched. We have an idea for an experiment that would tie in with some of our ongoing STEM activities like SuperSID and Radio Joe. Okay? And that is the fact that on Earth we have a lot of radio astronomy going on, of course, but a spectrum, part of the spectrum that cannot be monitored is typically the radio spectrum below about 10 megahertz, because the atmosphere is opaque to that frequency, that band of frequencies. It doesn't get through the atmosphere typically. So that is an ideal spectrum to be looked at using low Earth orbit or either high Earth orbit radio astronomy CubeSat. So we're not the only one with that idea, of course. Dr. Higgins from MTSU reminded me when I saw him yesterday that there is, India, is it?
Japan.
Japan, okay, sorry. Japan has a group that's currently working on a CubeSat with a similar mission in mind. I don't know exactly what the details, but we're going to find that out and maybe work with them. Dr. Fields over here, David, has been working on some ideas as well. And so there's a lot of things of interest at these lower frequencies. The heliospheric radio missions, solar burst, CMEs, planetary and exoplanetary radio emissions, galactic synchrotron emissions and cosmic rays. Lots of interesting things going on. Okay, Colin. This just shows how some of these things are related to planet emissions, and we happen to have a program, of course, everybody's familiar with, Radio Joe, and the experiment that Japan is doing, I believe, is going to be comparing signals received from Jupiter on a CubeSat versus what we're receiving on Earth. Compare the two, look, see if we can tell the differences and glean more information. So a lot of potential there to work up a really good science experiment. CMEs, we know that it's a danger to spacecraft, a danger to our power grid, all kinds of concerns about CMEs and how if we're not prepared for them, it could be a societal ending event for humans. So that's another area that we can consider, and of course that's supersid. We're not the first to think of this, of course. Up at Lincoln Laboratory of MIT, they're considering putting up a CubeSat version of the VLA using a swarm of CubeSats in an array and doing the same sort of things that we can do with the VLA, but in orbit, which would have a lot of advantages, hopefully, over what we're doing at the VLA. So, what would we do, or what would we propose to do if SARA were to become involved somehow, and not necessarily as an organization per se, but a group within SARA, possibly? Well, first of all, we would, as a primary objective, we would want to study this VLF, low frequency and HF reception. We'd want to store the data somehow and downlink it somehow, encrypt it or whatever, either on command or periodically. We would also have, of course, the system operational data like power consumption, temperature, attitudes, some things like that, I'm sure. But another secondary objective, very important, would be STEM activities. My interest is high in this area because I have a 7-year-old daughter who is in Athens, Alabama's first STEM academy. Just started last year. It's expanding to the whole elementary school level now, kindergarten through 6th grade, I believe, this year. And I got promoted to or volunteered to be the Alabama Academy of Science coordinator for STEM activities in our state. So that gives me some other resources and interests around the state on STEM activities. So I'm really pushing involvement with science, technology, engineering, math, and we're adding an A to STEM to make it STEAM to include the arts because, gosh, you know, us scientists and engineers don't always communicate our ideas very clearly, and so we have to depend on artists, writers, all that kind of thing to help us out. So these are some potential draft objectives and so forth. Colin? This would be just a simple block diagram of how it might work. We would have some sort of receiver, maybe a software-defined receiver that we could command to change frequencies and do different things, signal processing, some sort of storage, and then we would interface, we hope, with a satellite similar to the Vanderbilt satellite. AMSAT, typically, their Fox series consists of 10 circuit boards. 8 of those circuit boards have to do with the boilerplate necessary to control power, communicate, uplink, downlink, data storage, control, all that. So that leaves 4 circuit boards for the science experiment, one of which has to be an interface board between the experiment and the AMSAT equipment. So you have 3 circuit boards that you could put science on, and this is what Vandy does. And so we're working now to get an MOU with AMSAT. Jerry Buxton, their VP of Engineering, is working with us to do that. We're working with Vanderbilt to get a non-disclosure agreement in place so that we can share some of their proprietary CubeSat information. The reason it's proprietary, one reason is that a lot of their work is actually funded by government contract. They have some defense contracts they're working on, some NSF funded stuff, so they don't just give out the details of what they've done. willy-nilly, so to speak. So we hope to get that in place. But they've agreed, and AMSAT in principle has agreed to work with us as a group if we decided to do this. And it might be something like that. Okay, Colin? Who would participate? Well, we've been sort of beating the bushes out there to see who in the radio astronomy and STEM areas would be interested in working this kind of project. And so Florida Tech, my alma mater for space systems master's degree, Dr. Don Platt, who is the director of that program, has agreed to participate. He is a CubeSat experienced person. University of North Alabama, where the previous Alabama Academy of Science coordinator, Mel Blake, is interested. Dr. Shields and the TAO is interested. Spark Academy, I mentioned. AMSAT, Alabama Academy of Science. We've even talked to Lori Wingate a little bit about how we might incorporate this in with her internship program around the world. I have a friend who I used to work with in defense work who is the science curator of the Macon, Georgia Museum of Arts and Sciences. Paul Fisher has agreed to work with him. He runs their planetarium and lots of other stuff. Athens State, where I'm from, might contribute something along the way, and of course Vandy. So these are just some of the organizations who have expressed interest in playing. It is not a simple undertaking. When we're going into this kind of with an eye open to the fact that we're talking about several years of commitment to make this happen, so we don't go into it without thinking really hard about it. I'm like most of you people, I imagine, is when I start something, I like to see it finished, I like to see results. So we're trying not to jump into this without knowing for sure we can pull it off. Okay. Okay, so in summary, CubeSats do offer a unique opportunity to expand our radio astronomy into space and to particularly grow outreach in the STEAM area. My daughter, a lot of children and young teenagers and even high school, college students obviously are interested in space, radio astronomy, astronomy. Yeah, the disciplines are pretty well covered. It's a great thing for STEM. We hope we can pattern our experiment after some of the ones that's been already thought of and improve on them, learn from Vandy, AMSAT. We're not trying to reinvent the wheel. We'd like to use off-the-shelf hardware. And by the way, AMSAT has kind of hinted that there's some spare hardware available on their Fox program. If we can get our act together, we might have access to some of that. The only thing they're missing right now are the battery pack, the power batteries for the thing. So we have some opportunity there.
If you talk to Auburn, if that's not forbidden territory, you might get to know.
Talk to who?
Auburn.
I'm an Auburn grad. It ain't right, we'll talk to Auburn.
John Klingelhofer.
So anyways, the cost, we would have to, you know, I'm sort of a pull yourself up by the bootstraps type of person, but realistically, we're going to have to come up with several $1,000s probably along the way to make this happen. I think there's a possibility we can do some crowdfunding or raising funds along the way, but that's part of our decision. Vandy spent $120,000 on AO85. Most of that came from government contracts that they had in place with related use of radiation effects on semiconductors. And we hope that by playing off of what they've done, using AMSAT, spare hardware, all that stuff, you know, we might can pull it off for a lot less than that. So we are proposing that we put together a SARA special interest group. We collected names at the Western Conference, got probably a dozen names of people who wanted to consider playing the game. Any of you who have comments or ideas, we'd like to hear about it. So what we need to do is possibly formalize that SIG within SARA, and I'd like to say that this is not to solicit any formal funding or commitment from SARA as a group. What we're suggesting is we try to formalize a group of people who are interested and then go work the problem to see if it's something really worth doing. It's several years of work. The problem at the bachelor's degree level is that, particularly at our school, I mean, we run students through in 2 years, so you have to have a lot of participation longer than that. We've got the MOU and work with AMSAT. The NDA has been signed with Vandy. We're waiting for their legal department to kick it out. The next big thing to do, other than get a commitment for interest from SARA, is to possibly bid or submit a proposal on the next round of NASA launch slots. What they do at least once a year, I think it is, they solicit proposals from universities and educational, commercial, whatever. You propose an experiment, and all your mission, your capabilities, all this stuff, and they hand-pick organizations that they feel can be successful and are worthy. Once you get a launch position or a slot on a launch, then I think you're beginning to take this thing seriously with the other people in industry. If you're just talking about it like we are right now, it's sort of, well, yeah, everybody's got that idea, but do you have a launch slot? So one of our big things to push for is to do a proposal, see if we can get in the queue, and then go from there. Then continue some development. Dr. Fields and Ken Redcap has talked about the fact that we want to do a proof of concept demonstration, more than one, by maybe flying part of our hardware on a balloon, high altitude balloon, do some other things so that we can get a lot of confidence built up in our hardware, software, the basic mission profile. So a lot of work to do. We're still scratching our head that we really want to do this, but we'd like to get feedback from SARA. So with that, I'll open it up to questions from the audience. David Fields.
I've looked at what other people have done, and I'm really impressed by the number of good ideas. What is scary is the number of good ideas that don't make it. The number that make it is very small. What is the reason that these projects don't go ahead?
I believe it's just the overall commitment in terms of man hours, time, and such. So like I'm saying, we're talking up to a 5-year program. If we can jumpstart it by getting help from Vandy and AMSAT, we might have a 18-month program at best, probably. But it's not something you do overnight. So I think that's what it is, David. I think it's a big undertaking. The results are fabulous. I think it would do so much for SARA and all the STEM activities that we support, but it's not going to be easy, and I think that's what it's like starting a new company, you know. 1% of the new companies that start are around after a year. It might be that low in CubeSat development too, so it's just a big deal, really.
So we're talking here about the CubeSat, which is 10 centimeters by 10 by 10. I assume the orbit would be a LEO, a low orbit. I assume
that's one of the possibilities, but there are also the Vandy orbit, I believe, is around 600 miles. That's still considered to be low Earth orbit, but they're looking at also the possibilities of some GEO stuff. So it just depends. It depends on what slot we get.
Looking at the lower tab for the cost, I'm thinking about getting to the whatever is possible within a budget. I think there will be a LEO with 300, 400 kilometer high altitude, circling the Earth once every 90 minutes or so.
Right.
So consider those things, and probably on this, to minimize the cost, the CubeSat will not be attitude stabilized, so it will be tumbling in space. Turning back to the primary mission, what exactly do you think this CubeSat will do? You said that it's going to do some stuff in the VLF, LF, HF range. What exactly? For Earth signals or out of the Earth signals?
Yes. That's the most important part. This is where we are now, is mission planning. Exactly what Chip is asking. What are you proposing to do scientifically? I mean, after all, it's all about the science. If we can't come up with a really good science experiment, we will not be selected to fly anyways. So we've got to put all of our heads together like Chip is suggesting, learn what we can from the Japanese program that's going on, talk to Lincoln Labs. I mean, they've got a multi-million-dollar program underway for a swarm of CubeSats. I tell you one thing that's setting us aside and maybe a stumbling block, we're trying to do something on the very simple, basic level that AMSAT started doing 10 years ago or earlier. A lot of people who are involved in CubeSats now, they've moved on. I mean, we're wanting to start from, at the very basic level. They're looking at making the standard CubeSat now 3 units and having all kinds of cool capabilities and going to very high Earth orbit or even GEO, lunar orbit. There's looking at putting CubeSats in orbit around the moon, and even Mars. There's looking at putting CubeSats in orbit around Mars. So we're proposing something so basic that I'm afraid we may not get a whole lot of interest, but we may be able to get some traction with the Japanese people and still make something like that happen. But Chip is right. We have to have a fantastic science experiment, or it's not worth doing in the first place. I think we could make some good headway.
It kind of sounds like, with us being interested in low-frequency radio astronomy, and the ionosphere goes up to what height? Maybe 150 to 200 miles, something like that.
Right.
So it says that you're going to have to be in an orbit that's
above
fairly
that.
high, so you're above the ionosphere. Because if you're in the ionosphere,
exactly,
that whole thing ain't going to work. Can you select your orbit when they give you your?
I think you probably would propose your science experiment, and then based on your needs to validate or
So they would find a load going
right.
high.
Right. So if you get selected based on your science experiment, they'd probably put you in a slot that would accommodate the experiment. Otherwise,
Yeah, so they put you at 600 or 1,000 miles. That was they really work above the ionosphere.
Yeah, there's a big problem too of radio interference from Earth. That is the one thing that the people at Florida Tech are questioning. They say, well, how are you going to get rid, or how are you going to work around the extreme amount of RFI you're going to get from terrestrial sources? And the answer to that is put it on the dark side of the moon, right? Yeah. But that's not what we're proposing to do. So we're going to work that. Now, obviously, MIT thinks it's going to work with a swarm, so we got to get some smarts on what they're thinking about there, but yeah, exactly. So
well, stage one is, the atmosphere is opaque both directions. That we can't see from space.
Well, at the low frequency, that's right.
It's going to be hopefully,
But opaque is not opaque.
I know, it's not 100%.
Yeah, it might be opaque to the signals, but it's not opaque to the RFI.
Yeah, the other question is what's the orbit in terms of, oh, great, we're over the Atlantic an awful lot, or the Pacific.
Those are considerations, absolutely. You wouldn't want to fly over the, if you had a choice. If you had a choice, you wouldn't want to fly over a hotbed of radio interference, that's for sure.
Well, the typical orbit's going to be between 500 and 800 kilometers. Okay, and the downlink on a one U is probably either UHF or VHF. So
right.
the ionosphere is not. So your downlink's there, and Since you're above the ionosphere now, you can look at things that are absorbed by the D layer. And of course, the orbit tends to be polar orbits with inclinations of about 90 degrees. So you're going to fly over the whole Earth once a day.
And as you can see, we're blessed with the fact that we do have a lot of resources already within SARA that have some smarts in this area. So it's not like we're starting from dead zero, but we got a lot of learning to do, the critical parts, the mission plan, the science experiment. All this is a lot of brain power and paperwork before we start building hardware. David's already experimenting with antenna concepts and hardware, and we hope to demonstrate some of that on a balloon or such as that, just to say, hey, look, it might work, type of thing. But anyway, thank you so much for the opportunity, and if you have an opinion, you might mention it to Tom or to Mr. Redcap, and I think we're going to try to just maybe officially bless the idea of a SIG on CubeSats and see where it goes. Thank you. By the way, Colin gets $15 every time I use his picture. You'll see that in all my presentations. Thank you.
All right, lunch is at 12:30. We'll meet back here at 1:30. Call for an
ground microphone right now. Mind leaving it? Leave it stuff here, I suspect.